Hello there, and yeah, good morning. Yeah, I'm Steve Larter. I'm a geochemistry professor at the University of Calgary, and I'd like to welcome you to our webinar, Waves, Widgets, and Socially Desirable Technologies, Challenges of Ocean Cdr. So looking forward to an exciting set of talks and discussion. Many of us may be on the treaties of Indigenous peoples, and in Calgary, we take this opportunity to acknowledge the traditional territories of the people of the Treaty 7 region in southern Alberta, and the city of Calgary is also home to Métis Nation of Alberta, Region 3. So who's involved in the webinar? So our keynote speaker is Greg Rao, who's the co-founder and CTO of Planetary Technologies. From Dartmouth, Nova Scotia. He's also senior research scientist at UC Santa Cruz. Ben Tutelo is an associate prof of geoscience at the University of Calgary. Anna Maria Hubert is a professor of environmental law at the U of C, is also a research affiliate at the Institute for Science, Innovation and Society at the University of Oxford. Dave Sinton is a Canada Research Chair in the Department of Mechanical and Industrial Engineering at the University of Toronto. Matt Eiserman is a professor in the Department of Electrical and Computer Engineering at Stony Brook University. And I'm, as I've introduced myself, at the University of Calgary in the Department of Geoscience. So the program will go like this. I'm going to give a very brief kind of overview of the speakers, a couple of background scene setting slides, and then we'll get into the meat of the program. So the keynote is Ocean-Based Carbon Dioxide Removal, a Planetary Perspective by Greg Rao. Then we'll hear a talk from Ben Tutelo on marine carbonate alkalinity and the potential of large-scale submarine basalt carbonation. Critical to the whole area of CDR and Ocean CDR in particular is the integration of governance, regulation, policy, and so on into the space. So we'll be hearing from Anna Maria Hubert on developing responsible governance in the marine CDR space. We'll take a short break, and then we'll hear from Dave Sinton about electrochemical routes to CO2 capture and conversion. And then the program will be finished by a talk from Matt Eiserman on electrochemical ocean alkalinity enhancement for ocean acidification. So you can see there's a strong electrochemical theme, but we're also going to be looking at other geochemical routes to CO2 storage with Ben, and then we're also looking at governance and regulation issues. And finally, we're going to have a Q&A back and forth on issues that have emerged during the presentations. So I was asked when we were setting this up, what's happening at Calgary, and for those that probably know something about us but don't know all, here's a quick infomercial. So carbon management at the U of C has a long history. We've got many research groups active in STEM, law, policy, and social science areas. In 2009, we set up a not-for-profit organization called Carbon Management Canada. I was the first science director of that. That has a field site in Brooks, Alberta, and if you look on the top right diagram is the current scientific director, Professor Don Lawton. We have a shallow storage test facility that's basically developing MMV type technologies. Notable innovations that have come out of the University of Calgary carbon management programming include, carbon engineering and David Keith, now at Harvard, and George Shimizu, his MOF group, developing these metal organic framework sorbents that are now being commercialized at scale across the world. We've got several projects relevant to today's seminar. One is the Solid Carbon Project hosted at the University of Victoria with Oceans Network Canada, and Rachel Lauer and Ben Tutelo are part of that. We've got a series of people working on, I've just got a few this central picture here. people involved with some of the big research projects in Alberta, like Quest. We've got Jewel Bergeson, Ming Zedong, Nigel Banks. So these are not just scientists and engineers. Nigel Banks is a lawyer, heavily involved in CCS regulation developments in Alberta. Sean McCoy, Stephen Bryant, and then top left is Paul Tawaya, who defended his PhD successfully at the end of last year. He's now gone on to start his own CCS company. So a lot of activities. The other project we've got is this Peach project, and you'll be hearing from Ben and Anna Maria today, who are part of the Peach project. That's our Ocean Cdr project. And if you want to know more about that, you can look at the link at the bottom, the Climate Solutions link. We're also been heavily involved with facilitating innovation and startups in this climate tech space. A lot of people at the U of C involved with the Creative Destruction Lab, both the Energy Stream in Calgary, CDL Rockies, and the Climate Stream in Vancouver. And the University of Calgary is also involved with Avatar and X Prize on their carbon removal accelerator, promoting technology in this space. So I think we all know the background. The diagram on the right is Canada's emissions profile, and we know where we want to be at 2050 and 2030. We know what we have to do, and we know that negative emissions are part of this story. I think for today, we'll be hearing relevant discourse on several of our challenges. One is this research to solutions. We need more solutions faster. We need governance embedded in the programs. More innovators are needed. We need institutional change. The timelines for, whether it's industry, government, or universities, we're just too slow, too long timelines to really deliver the solutions we need in the timelines that are upon us. We need totally new business models, multi-sector collaborations and investments. And then a little slide from PwC looking at the immense amount of clean tech investment that's going into climate tech space and how that's impacting research and development. So we've got to socialize, discover, invent, develop, pilot, and deploy technologies far faster than we've ever done before. So today, very high level slide here, 3 general routes to CDR in the marine space. One is modifying surface water alkalinity. We're going to hear a lot about that today. There are also routes to involving the organic ocean carbon cycles, looking at, dissolved organic matter conversions, looking at taking biomass from the surface and sinking, preserving it into sediment reservoirs, or adding biomass-derived stable organics to DOM. We're not going to really talk about that today. And then finally, we're going to hear from Ben about injection of CO2 to subsea seafloor reservoirs, including reactive reservoirs such as basalts. So with that, we'll get into the main program, and we'll hear from Greg on ocean-based carbon dioxide removal, a planetary perspective.
Well, thank you, Steve. Hello, everybody, from my home here in the East San Francisco Bay. Let me see if I can get my slide deck up here. Oops. There we go. I assume everyone can see that and can hear me. Thank you for inviting me to speak here today. I've known University of Calgary as a real leader in the CCS and direct air capture space. So thanks for the reach out and wanting to learn more about the Ocean Cdr potentials here. I think my task here is to just sort of give you a planetary or global perspective from my point of view on Ocean Cdr. And toward the end of the talk, I will also give you a view of what Planetary Technologies is doing in this space. So I assume I don't have to make the case of why we need CDR. Obviously, we have failed to stabilize atmospheric CO2 concentrations at safe levels. And we continue to fail to do that. And we now need to seriously consider how we're going to reduce the atmospheric CO2 burden much more quickly than would naturally otherwise occur if nature were left to its own devices. So now we not only need to reduce our emissions, but we also need to think about actively removing that legacy CO2 that we've emitted and will continue to emit. Certainly the third option here is to consider climate modifications as well as adaptation. Obviously, that's a separate subject for another seminar, but I also think we need to be seriously considering those options in the, given the uncertainty as to how effective our atmospheric CO2 management is going to turn out to be. So why Ocean Cdr? Well, first off, historically, as we know, the Earth or the emissions, our emissions have more than half of has been absorbed by ocean and land processes. So CDR is not a new concept. It's something that Mother Nature naturally does, thankfully. And as I say, as a consequence, less than half of our emissions actually ultimately stay in the atmosphere. And it turns out that oceans do a major part of this uptake. And so for reason number one, the ocean is already doing CDR. And then the question is, well, can we safely and cost effectively increase this natural uptake? I might also say that this uptake, the nature of it is causing ocean acidification. Actually, the uptake is due to the difference in partial pressure between the atmosphere and the ocean. It's forcing CO2 into the ocean, which then hydrates and acidifies the ocean. So we don't want to replicate this method of CDR. We need to think of other ways rather than just stuffing more molecular CO2 into the ocean. The other argument for thinking about ocean CDR is the fact that most of the carbon that's in communication with the atmosphere is actually in the ocean. 85%, 88% of the total surface carbon is in the form of bicarbonate and carbonate ions in seawater. So clearly Mother Nature has made a choice here and clearly prefers to store the carbon in the ocean in seawater. And it might be wise to figure out ways that we might want to enhance that storage capability. So, the ocean plays a major role here in the CDR that's going on and in carbon storage. So we should seriously think about ways that we could safely and cost effectively increase that. So how has Ocean Cdr been received by the larger policy and science community? Well, there was a major publication by the National Academy putting out an agenda for CDR, at least for the United States. And for the most part, the oceans were ignored in this report. Lots of money were proposed and various primarily land-based ideas were discussed. The one ocean aspect of this was coastal blue carbon, which involves things like mangroves, seaweed, seagrass, et cetera. But the vast majority of the potential for the ocean to play a role in CDR was ignored here. And I and others were not too pleased about this, and I told the National Academy about this. Unfortunately, this last December, of course, they convened a committee some years prior to this, and they did generate an Ocean Cdr agenda, and hopefully have rectified the absence of Ocean Cdr in the earlier plan. And this report, goes through and discusses in some detail various approaches to Ocean Cdr, what should be pursued, and gives some priorities in terms of R&D. And it's no doubt this report that has precipitated sort of renewed interest in Ocean Cdr, and probably was played a role in University of Calgary getting interested in this realm as well. So anyway, it's good to see that the absence of Ocean Cdr earlier has been rectified by a renewed interest in this field, and thanks to the National Academy and to ClimateWorks Foundation for pursuing this report. Now, in terms of a taxonomy for CDR, there are sort of three different approaches that you can take in this, and I've just say here physics, biology, and chemistry. But keep in mind that there are overlaps, and there's some very interesting approaches that can be used or can be explored that at the interfaces and at the overlaps of these disciplines. And something we have to keep in mind, it's not necessarily, we don't have to strictly follow a particular discipline. Some of the most interesting and low-hanging fruit for CDR could actually be at the interface. And that includes thinking about synergies between land and ocean. We don't have to do strictly Ocean Cdr or land CDR. There can be interactions there. You can do the capturing on land and you can do the storage in the ocean, and vice versa. So I'm an advocate for trying to be sort of technology neutral here, and how do we pursue it? The real goal here is to find safe and cost-effective ways and high-capacity ways of consuming and storing CO2, and that could happen on land, in the ocean, or some combination thereof. So I'm going to start with the biological approaches. Obviously, biology plays a big role in modulating atmospheric CO2. We know that because when we look at the atmospheric CO2 concentration at an annual cycle, there's actually the actual atmospheric CO2 goes down. And that's largely due to photosynthesis. And during the growing season, clearly plants are converting CO2 to biomass and actually doing CDR. Unfortunately, most biomass is not very long-lived, and there is a reverse reaction where the biomass gets respired back to CO2, and so you get a dramatic increase, intra-annual increase in CO2. But clearly, either or both of these, trying to manipulate these, could be useful in managing atmospheric CO2. Could the plants take up more CO2, and/or could we reduce the recycling of that CO2 back to the atmosphere? And that's largely the approach that's taken in marine biological approaches. Can we either restore photosynthesis that has been lost, and this has especially been pointed out in the blue carbon field, where coastal ecosystems have been impacted. The biomass has been reduced, the standing stock of biomass carbon, and so certainly one approach here is to actively try to restore photosynthesis and standing stocks of biomass in those areas. Beyond that, we can think about actually increasing photosynthesis, or again, reducing respiration in the ocean. There are a variety of ways of doing that. We can fertilize the ocean, upwelling, aquaculture, etc. The one feature of this is that when we do make biomass, we have to figure out how to make it long-lived, or long-lived enough so that it makes a difference in atmospheric CO2. And there can be ways of converting that biomass to useful products like biochar, plastics, etc. So the issues here, as I guess I've already said, most marine biomass quickly degrades. It actually needs to, because marine ecosystem needs to recycle its nutrients. It doesn't want to lose nutrients out of the photic zone by sinking of biomass. So it's been adapted to be a very efficient recycler, and that includes efficient recycling of carbon. And we need to think about ways of possibly modifying that scenario so that there is more storage and less regeneration. If we are going to produce a lot of biomass in the surface ocean and then sink it away from the atmospheric system, so there's some amount of storage, we always have to worry about, in effect, organic loading of the deep ocean. That's going to consume oxygen, it's going to generate CO2, it's going to generate acidity. So just producing a bunch of biomass in the surface and sinking in the subsurface ocean and not actually burying it and getting it out of the seawater, or otherwise getting it out of the seawater, is not, that could be very impactful to the rest of the ocean. So we have to be careful about where we store this organic matter that would be produced. Clearly, you need to supply additional nutrients if you're going to increase photosynthesis. It's not a matter of just increasing carbon uptake. There are nutrients that go along with that life requires. So we have to think about managing that. We always have to think about how any sort of increase in photosynthesis is going to impact the marine ecosystem. Are we changing species? Are we changing the function of the ecosystem, et cetera? So that always has to be considered. And there's also the issue of how do we actually verify the amount of carbon that we would mitigate by this process. And since we're adding potentially a small amount of carbon to a very large pool, this could be a real issue of how we actually measure and document that feature. So the bottom line here is that if we're going to go if folks are going to go the biological route, we do need to find out a way of safely doing this, as well as being cost effective. And my view is that this is going to require some serious management of biology. I don't think you can just fertilize the ocean and hope for the best. It's going to require some careful management of growing the biomass, harvesting it, and carefully storing the carbon and separating out and recycling the nutrients if you can. So there's a lot of work to be done here, I think, to proceed. Another, a more physical approach here would be to simply extract the CO2 that's in the ocean. The idea here is if you can extract it, then the ocean is undersaturated in CO2 relative to air, and it will take up then additional carbon and store it. And presumably you will have stored the carbon that you have extracted. So there's a couple ways of doing that. You can obviously apply a vacuum to the ocean, to seawater, and suck the CO2 out, or you can purge it with a CO2 depleted gas. Both of those obviously are energy intensive. One thought I had was that if direct air capture becomes very widely used here, you've got a CO2 depleted stream that in theory you could use as a purge gas to strip out additional CO2 from the ocean. But that's just an idea here. The other approach that's been explored, and presumably Matt will talk about this further, is using electrochemical means, basically acidifying seawater. When you acidify seawater, you shift the carbonate chemistry in favor of CO2, forming molecular CO2. You supersaturate that seawater, and the CO2 will come out. And if you're able to store that carbon, then re-equilibrating that CO2 depleted seawater will then take up additional CO2 from the atmosphere. So the issues here is probably a very energy intensive process, and it's going to require some renewable energy to really maximize the negative emissions aspect of this. There could be downstream environmental consequences of removing the CO2. You are modifying the chemistry, although that could be ameliorated as it re-equilibrates with air. You're going to have to store the CO2 that you've removed. So just as in CCS and direct air capture, there's got to be some long-term storage plan there. If you've undersaturated the seawater, you of course hope that completely equilibrates with the air, and you've maximized the amount of transfer of carbon from the atmosphere to the ocean. But that assumes that water is going to stay in contact with the atmosphere, and because the ocean is in motion, that may or may not happen. So you do have to be concerned about that water, the fate of that water once you have undersaturated it. You want to make sure that it stays at the surface and maximizes the uptake of carbon from the atmosphere. course, you want to be able to verify that you've done all this, that you've stored the carbon and you've taken up the CO2. And my view is here, this may be applicable at local scales, but let's find out. Let's see what we can do. Let's see what the costs are, and perhaps this could ultimately contribute to a larger scale CDR efforts. The last approach I'll talk about is chemical, and here I want to focus on enhancing ocean alkalinity. This is really just acid-base chemistry. We have an acid in the ocean, carbonic acid, and by adding a base, you can neutralize that and you convert the CO2 from an acidic form to one that's neutralized and bicarbonate and carbonate forms that are balanced by metal ions such as sodium or potassium or magnesium, etc. And when you do that, you undersaturate again the CO2 concentration in the ocean, and that then forces uptake of additional carbon from the atmosphere. So you've increased the dissolved inorganic carbon in seawater by initially shifting or consuming the existing CO2 to bicarbonate and carbonate, which allows additional uptake from the atmosphere. So the CO2 reactive bases that we could use to do this, clearly there's synthetic, and then there's natural forms. The synthetic forms have the advantage that they are very reactive. They are, they react quickly. The kinetics are fast. They can be pure, but there's not a lot of other stuff in them, or they can be made to be pure. Downside is that they are usually energy intensive to make and costly. On the other side, there are natural alkaline materials. Silicate minerals have been at the top of the list for a while. You can grind them up finely, add them to the ocean, and consume CO2. One of the equations there is at the bottom. The issue here is, while these are cheap and inexpensive, they are very slow reacting. And so various methods are being considered as to how you might accelerate that in the context of marine CDR. So again, the issues here, you're probably going to need some energy input here. You want that to be, well, you may need some significant energy input. You'd like that to be, carbon neutral energy. There will be chemical impacts to this approach. You are going to be changing pH. You're going to be elevating pH. Ultimately, there can be contaminants in the alkalinity you add, so you have to be careful about that. And so just as ocean acidification has enjoyed a lot of research in the past decade or two, I think now that the interest is shifting in the other direction. So what are the effects of raising the pH, adding alkalinity to seawater? And so there's a large effort afoot to better understand that. There are also potential upstream impacts to this because you need a source of alkalinity. Those are typically derived from land, and so there can be environmental impacts there in making or extracting alkalinity. You've got to move masses around. You got to move if you make alkalinity in one place and it's not near the ocean, you have to move that. So there's some logistical considerations. And there's also MRV. How do you confirm that you've safely stored this stuff in the ocean for X amount of time? There is natural ocean alkalinity enhancement. This is actually one of the primary ways that Mother Nature consumes excess atmospheric CO2 on geologic timescales. This is why seawater is so enriched in bicarbonate and carbonate ions, is because of the weathering of rocks by water and CO2 to form bicarbonate and carbonate ions, balanced by cations other than hydrogen. So non-acid alkaline carbon is added to the ocean. So we need to think about ways that, again, how we could accelerate this otherwise natural process. And one way to do that is to generate alkalinity by electrolysis. And basically what this is when you electrolyze a salt solution, you do four things. You split water to make oxygen and hydrogen, and you make an acid and a base. Typically, when you do this just for the hydrogen, the acid and base neutralize internally in the cell. So there's no net change in pH. But for our purposes, since hydroxide is valuable as a carbon removal agent, we wanted to, rather than neutralize that with the acid, we want to separate the acid and base and use that hydroxide in an Ocean Cdr scheme. This leaves the acid behind. And of course, you could use that in commercial applications, but that probably would quickly be swamped if we were to do this at large scale for CDR purposes. So one way to neutralize acid on a large scale is to simply do that with alkaline rocks, which are very abundant on the Earth's surface. So that's the basic strategy. Various people have come up with various variants of this idea, starting with House et al. In 2007, which was the first real foray into electrogeochemistry for purposes of doing CDR. And again, the point, the idea that Planetary and others are pursuing is that we're producing this hydroxide. We want to react that with atmospheric CO2 by adding that hydroxide to the ocean, and thus partitioning a little bit more carbon out of the atmosphere and partition that more into the existing already large bicarbonate and carbonate reservoir in the ocean. And so, you know, Planetary's particular approach here is that we take water or renewable electricity and alkaline rock tailings, and we put that into an electrochemical process. We remove the other valuable metals out of that system. And what we ultimately make is an electrolyte. It's actually magnesium sulfate as an electrolyte. And so we split magnesium sulfate and water to make hydrogen and oxygen, and also our hydroxide. And our acid is recycled back to the alkaline rock material so that we can remove additional metals and make additional electrolyte. So as you can see here in this image, this is not just about CDR. We're doing other things as well. We're making green hydrogen. Of course, we're using renewable energy. So as in any electro hydrogen system, the carbon footprint of the hydrogen is low. We're also removing valuable metals, in particular, in our case, nickel and cobalt, which are very important for batteries. Obviously, they're important for transportation and energy storage. Silica can also be recovered. This is something that we're not actually actively pursuing now, but there could be, this could be a source of silica. We're also reclaiming mine waste because the material we're using is an asbestos tailings, and our process actually removes and neutralizes, decomposes the asbestos. So there's a mine reclamation element to this. And of course, adding alkalinity to the ocean helps us counter ocean acidification. So it's really a platform for doing multiple green things, in addition to doing CDR. This is a little more detailed schematic of what we're doing. Again, we're taking our acid from our electrochemistry, and we're using that to extract metals and make metal salts that most of which we extract, but we leave the metal, the magnesium sulfate behind, or in purified magnesium sulfate to use as our electrolyte, and our end product is actually a solid magnesium hydroxide. So by our calculation, we're probably consuming, say, 20 tons of CO2 per ton of hydrogen generated here. So it is a carbon negative hydrogen generation scheme, among other schemes. Our aspirational energy use here, we're looking at probably 6 megawatt hours per ton of CO2 consumed. So it's no bargain in terms of energy. But actually, it turns out most of that energy is used to split water. Only about a third is used to make the acid and the base. So perhaps we're allowed to say that maybe even as little as 1 megawatt hour is required per ton of CO2 removed. As a point of reference, I think direct air capture, the figure is of like 2.5 megawatt hours in a combination of electricity and heat. So what about costs here? Obviously, we're doing a lot of things. This is not cheap to do, and our gross CDR cost is going to be hundreds of dollars. But keep in mind that we are producing a bunch of valuable product as well. So the net cost here is potentially quite low, even though we're putting a lot of energy into it. We're doing a lot of things here. And the value of those things could significantly offset the cost. So it's possible that we can have really a very low cost and net cost in doing this with respect to CDR. Does adding magnesium hydroxide to seawater really affect CDR? And the answer is yes, at least here at beaker scale. We did a series of experiments, and they're actually ongoing, where we added solid magnesium hydroxide to seawater. And you can see in the left-hand image here, we get a dramatic increase in alkalinity as expected. And likewise, we get a dramatic increase in pH. But that pH drops off as the CO2 becomes undersaturated in this solution and CO2 starts invading from the atmosphere. This counters the high pH that's initially affected by the high alkalinity. And at the end of the day, we increased the total dissolved inorganic carbon by about 50% in the seawater after, say, 600 hours of exposure to air. So this does work. It does consume CO2 from air. It is stable in air, and it does ultimately elevate, beneficially, hopefully, elevate the pH of the receiving seawater. Just this week, we've decided to up our ante here and look at a much larger scale beaker experiment. This is the Aquatron at Dalhousie University. Many thousands of liters of water here, and we instrumented the tank and released a plume of magnesium hydroxide here. We're still working on the data, and we'll be doing more experiments, but this is just to show that we're getting into larger scales here, and we do need to better understand the chemistry and physics involved here before we really go out into the ocean. And that brings up the point of MRV. In other words, if we were to do this in the ocean, how the heck are we going to verify that we've actually taken up carbon, and this is an effective way of doing CDR? And this is, admittedly still needs a lot of work, but you can imagine that we want to measure various chemical parameters, most importantly, any increase in dissolved inorganic carbon, and to integrate that over time and space and ultimately come up with an estimate of the amount of carbon that we've removed from the atmosphere and added to the ocean. Drones and sensors are going to play a big role in this, and there's a lot of work to be done here, but we have some confidence that we'll be able to come up with an acceptable way of quantifying and verifying that we can do CDR in this manner. Just a shout out to our team here. Mike Kellen is our CEO. And we have two teams, the blue team and the green team. The blue team is involved in the ocean side of this, and the metallurgy and EChem are dealing with the upstream production of our hydroxide. It does involve several universities, Dalhousie in particular, and PML at Plymouth Marine Lab and the University of Miami. So thanks to them for their partnership, and the team is growing, and we hope to do eventually soon be in the ocean and do some large scale testing. So just to wrap up, the ocean has considerable potential to contribute, to help us do CDR by various means. Obviously, we're in the early stages here of finding out what the possibilities are and what their characteristics are in terms of capacity, safety, cost, et cetera. And there's a lot of research and development needs to be done. We certainly need to have methods, acceptable methods of verifying that this is safe and effective. And most importantly, we need political policy and market support to really make this happen. Without that, this isn't going to go forward. And hopefully now that marine CDR has come to light in some circles, some important circles, hopefully we will be able to fully evaluate the marine's potential here in helping us manage our atmospheric CO2. So thanks for your attention. Hopefully there's a little time left for questions. If not, please get in touch. Happy to talk anytime. And thanks again for inviting us to speak here today.
Yeah, that was awesome, Greg. Thanks very much. So there is time for some questions. If anyone's got a question, you can put it in the little Q&A thing or raise your hand if you're on the panel. No, I've got two questions really. One is some idea, you're very sensibly, you've got multiple products envisaged in the overall program. You've got an onshore facility. You're looking at kind of already permitted outfall plans. What's the likely scalability, assuming that your system works as planned, what's the magnitude of the impact you think this approach could have globally in terms of CO2 reduction?
I think the limitation is probably the availability of renewable energy.
Okay.
I think that's probably a limiting factor. But there's a lot. We're actually not limited by renewable energy. There's plenty around. And I actually had a slide that I removed that talks about, for example, renewable energy, ocean energy. There's 5 or 6 times or more the potential renewable energy potential in the ocean than when we consume globally. So there's a lot of renewable energy out there. It's just not always cheap and available when and where you want it. So my view is that availability of renewable energy is a limitation in the approach.
So there's a question from Nicholas Des talking about, you talked about permitted ocean outfalls. Mm-hmm. Could you please develop on what are the current restrictions, conditions, and how Planetary is addressing them?
Yeah, well, thanks for bringing that up. I actually didn't emphasize how and where we were going to add the magnesium hydroxide. And our initial effort here is existing outfalls to the ocean, either municipal sewage outfalls and or power plant outfalls where power plants use seawater as a cooling agent. So either or both of those are what we're initially going to pursue. The limitations are, as we see it, come down to pH and turbidity. These types of outfalls are limited by how high the pH can be. Typically, it's at pH 9. I think in the UK, it's 8.5. But clearly, that's going to limit the concentration of alkalinity we can add to any given volume of water. Now, one advantage of us using our solid magnesium hydroxide is that it's really kind of a slow release form of alkalinity. And that's beneficial for us staying below that pH 9. And it allows more or less a much slower release of alkalinity and much less of an initial chemistry modification of seawater than would, say, adding a sodium hydroxide or some more soluble hydroxide. So that's our plan for discharging it, and that's the form that we're taking. We're going to be adding it as it probably will be a slurry or as a powder that we add the material. And we do need to stay below within permitted pH and turbidity limits.
Okay, yeah, thanks. Yeah, so final question from me. Not sure if what you can comment on. You've got a magnesium system electrolyte, and that's presumably somewhat related to your feedstock materials. But why? Anything you can say about why you've chosen that magnesium sulfate electrolyte system?
Yeah, well, we've decided that we wanted to make a solid hydroxide rather than something like sodium hydroxide or potassium hydroxide. Magnesium is very abundant in alkaline rocks, and you can extract it, as I said, with acid. And so it's an abundant cation, or can be made an abundant cation through acidifying rock tailings. And so for those reasons, we've struck upon this magnesium hydroxide. It's not the only possibility. There are other potential salts that we could use. I mean, I would say the ultimate salt here would be sodium chloride, because obviously that's very abundant in seawater, but the issue there is the chlorine generation. Any chlorine salt will generate chlorine rather than oxygen preferentially, although there are various ideas on how to reduce or eliminate chlorine generation in that kind of electrochemistry. But until that comes along, we're going to stay away from chloride salts as an electrolyte for that reason.
Okay, thank you very much. Okay, thanks. So we'll switch gears now and hear about marine carbonate alkalinity and the potential of large-scale submarine basalt carbonation by Ben Tutelo. So I'll hand it over to Ben.
I'm coming, I promise. Here we go. All right, let me just share my screen here. Zoom is, of course, being uncooperative. Here we go. All right, so thanks everybody for coming out today, and thanks Steve for the introduction. So yeah, I want to talk about marine carbonate alkalinity and the potential of large-scale submarine basalt carbonation. My name is Ben Tutelo. I'm a prof at the University of Calgary. I'm also part of the Solid Carbon Project, which I'm going to talk a lot about today, in the Peach Project here at the University of Calgary, which I'll also mention. So as anyone who has participated in the academic endeavor realizes, that this work doesn't happen in a silo. I want to mention that at least my part of the Solid Carbon team here at the University of Calgary includes a lot of really wonderful people. They're all listed here. And some of them are postdocs who are moving on and hopefully continuing on this work in their postdoctoral positions. And then others have gone on to graduate school and so on. So I want to thank them. And then secondly, I want to thank the Peach team, which has been instrumental in organizing this this seminar today or webinar today, and includes people like Steve, as well as lots of wonderful workers, including the electrochemistry team, who are really the nuts and bolts of the operation for sure. So I want to think, we're talking about ocean-based carbon dioxide removal. So I'm going to just think about the oceans here. So this is a photo I took aboard the Atlantis research vessel. That's the research vessel that houses the Alvin deep submersive vehicle. So the Alvin is if you've ever seen folks in a submarine exploring hydrothermal vents, that's Alvin. And I had the opportunity to be on Alvin back in 2016. And at that time, I got to see this plethora of basaltic material that exists on the ocean floor. So this is me taking a picture out the window of Alvin, looking at these things that we call pillow basalts. And so what happens with these pillow basalts is they're basically erupted at mid-ocean ridges. There's submarine volcanoes that are just pouring this lava onto the sea floor. And then over geological time, this basalt interacts with carbon dioxide in the oceans. So that's carbon dioxide that's ultimately removed, as Dr. Rao just said, from the atmosphere through nature's own carbon dioxide removal process. That water circulates into the oceanic crust and through on-axis hydrothermal systems, as well as off-axis, so in sort of the oceanic basins, warm fluids moving through the oceanic crust and bringing that CO2-rich seawater or alkalinity-rich seawater into the subsurface, reacting with the basaltic minerals. We're thinking things like olivine, plagioclase, and pyroxenes. And what happens is those minerals dissolve, they donate calcium, magnesium, and iron into solution. That calcium, magnesium, and iron combines with this alkalinity in the form of bicarbonate and seawater, and they make minerals like calcium carbonate. So this is a calcite vein shown in this diagram from my colleagues at the University of Victoria. So essentially, over geological timescales, part of what balances the emissions of CO2 from the solid earth into the atmosphere from volcanoes is this weathering of basaltic minerals on the seafloor. So the seafloor is actively taking up the carbon dioxide from ocean waters. And over human timescales, what we hope as part of solid carbon is that basalt carbonation, this process of turning basaltic minerals and seawater alkalinity into calcite and other carbonate minerals, can help mitigate the worst consequences of climate change. So there's technologies that are actively being used right now, such as the CarbFix project in Iceland, where they're capturing CO2 either directly from the atmosphere through a direct air capture machine or from their geothermal power operations, and then injecting that into aquifers on land, basaltic aquifers on land. And solid carbon, what we're working on is taking CO2, taking these equipment out into the oceanic environment or the marine environment, injecting that CO2 into the subsurface underlying the ocean. So those same basalts I showed whenever I was in Alvin. And importantly, and this is perhaps the most exciting thing about solid carbon and the potential of submarine basalt carbonation, is the enormous capacity, the enormous potential storage reservoir here for basalt carbonation. So this is an estimate given in a paper from a number of years ago now, where they estimate that anywhere between 100,000 and 250,000 gigatons or billions of tons of CO2 can be sequestered or stored in basaltic aquifers around the globe. And that means essentially that we could burn all of the fossil fuels that exist on the planet, take every single hydrocarbon molecule that is buried in subsurface reservoirs today, burn them, produce all of that CO2, and all of that CO2 that would be produced is approximately 18,000 billion tons of CO2, and still have extra space to put more CO2 into. So that's, to me, the most exciting thing about solid carbon, is the enormous potential capacity for storing CO2. So how solid carbon will work, so in our envisioned plan that we're working on right now, is we're using some sort of direct air capture device in the marine environment to capture CO2 directly from the atmosphere. Alternatively, we could take, a shipment of CO2 in a tanker or a pipeline. But in this envisionment, we see it directly capturing CO2 from the atmosphere, and then using something like wind or solar or tidal energy to power these direct air capture devices and the pressurization pumps in order to then inject this CO2 down below the seafloor, and then allow that CO2, once it hits into this basaltic aquifer, which is porous and permeable, to react with the aquifer fluids, so modified seawater, and ultimately become calcium carbonate. And so once it becomes calcium carbonate, then it has no more potential to enter into the atmosphere and contribute to our greenhouse gas effect. Win-win, right? So that we don't have any more heating or warming driven by that CO2. And solid carbon, importantly, as opposed to the CarbFix type technology, relies on supercritical CO2 rather than dissolved CO2. And the point is made nicely here in these plots here. So essentially, in order to get CO2 carbon dioxide removal at this needed gigaton per year scale, what we would want to do is dissolve the CO, or if we wanted to dissolve the CO2 into water, the energetic cost, which is shown in this right-hand plot here, kilowatt hours per ton of CO2, between CO2 alone, which is the purple line here, and CO2 plus water is enormous. It's not quite double, but it is significant. So this is a significant energetic cost that would require all of this additional offshore wind, et cetera, in order to drive that pressurization process. So in order to save on that energetic cost, we propose just injecting the CO2 directly rather than in dissolved form. And so that's why we rely on that. So what are the implications of this? So it isn't, I think the take home message that I can leave you with today before I show exactly why, is that it is not going to be as efficient as what has been shown in the CarbFix project in Iceland. So in Iceland, they've shown that CO2 mineralizes in their wells or in approximately 2 years. So all of the CO2 that they inject mineralizes in approximately 2 years. Our simulations and other results based on this supercritical CO2 injection suggest that it could be significantly longer in our circumstances. So, and the reason for that is emphasized in the schematic diagram here. So when we inject supercritical CO2, as emphasized by these bubbles here, the CO2 must first dissolve. So that's the first step. So step 0 being CO2 injection. And then step 1, CO2 dissolves into water. Once that CO2 dissolves into water and makes into a semi-acidic solution, it then drives basalt dissolution. And then finally, this basalt dissolution needs to reach a point where you supersaturate carbonate minerals and you can make calcite or calcium carbonate, as is shown in this figure here on the top right. And importantly, as any folks that have ever used an acid in order to clean out their tea kettle would know, carbonates are much more soluble at low pH or high partial pressures of CO2 than they are at atmospheric partial pressures of CO2. And essentially what that means, and the take-home message is that you need to dissolve much more basalt whenever you have supercritical CO2 injection to make the same amount of carbonates than if you were just using dissolved CO2 injection. So this message might be, so to increase CO2 mineralization, we just need to inject less CO2. And I say grimace emoji to that, right? Because if we do that, if we inject less CO2, then we're not going to be able to get to this gigaton per year scale as efficiently. So we need to find ways of injecting CO2 differently or in better ways in order to get CO2 mineralization at the scale we need. So, and I just want to show some simulations to emphasize this, right? So carbonates are less soluble at high alkalinity, regardless of the solution's partial pressure of CO2. So this is just showing plots of calcium carbonate solubility in calcium concentration as a function of partial pressure of CO2 and temperature. And what you see is that if we have normal alkalinity, so seawater alkalinity, this partial pressure of CO2 increases solubility quite significantly as you increase the partial pressure of CO2. Whereas if you are looking at a highly alkaline solution, such as that which is used in many carbonation experiments to look at these processes, you see that the solubility is decreased by at least an order of magnitude in those situations. And what actual difference does this make? And this will bring me to the final types of simulations that I want to work on today. Normal seawater alkalinity versus if we just arbitrarily increase the sodium concentration by 5% and then allow the charge balance to absorb more carbon dioxide. What we see is these primary minerals of basalt, olivine, clinopyroxene, and plagioclase become dolomite and anchorite over time. So this is normalized time to react an entire kilogram of basalt. And on the right-hand side, if we arbitrarily increase the alkalinity, we increase the amount of dolomite and anchorite that we make. So what does that mean? That means that increasing the initial alkalinity means that carbonate and dolomite and anchor in this case are going to precipitate earlier and in more abundance. And so I'm going to drive that home here in a minute. Unfortunately, and the problem is that subsea floor basaltic aquifers have slightly less alkalinity than seawater, not more. So what we need to do in order to make this happen more efficiently is to think about ways of improving this alkalinity budget. So again, coming back to the global scale, thinking about basalt carbonation, we've been working as part of Solid Carbon on this Cascadia Basin pilot site out in the Pacific Ocean off the coast of Canada in Vancouver Island. So the idea is that this is the most well-studied basaltic aquifer in the world. So there's been lots of integrated ocean discovery programs out there doing borehole drilling. There's the Ocean Networks Canada cabled observatory going out to this site. So we know a lot or more about this site than we know about any other basaltic aquifer on the planet. And so it's site number 1 for oceanic basalt carbonation implementation. And so what we've been doing is simulating this, and we've been really working hard on trying to get better and better estimates of reactive transport models, or making better estimates to fuel our reactive transport models of these carbonation reactions. So in these simulations I'm going to show right now, we inject 500,000 tons of CO2 per year for 10 years. That is about half the rate that we would propose to inject at a fully implemented scale. And then we're going to examine this impact of varying surface area estimates on CO2 mineralization. And the reason we're doing that is because that is the #1 parameter that's generating uncertainty in these large scale simulations. And so this is just an example of a standard characterized surface area injection of CO2. What you see is that the CO2 is injected, it dissolves, and eventually goes away. So we inject CO2 for the first 10 years, that CO2 dissolves, and then once it dissolves, it begins to mineralize. And so here's the plots of mineralization in that same simulation. You see we're forming dolomite in the area surrounding our well, magnesite. So this is calcium magnesium carbonate, iron carbonate, and calcium iron carbonate, all forming in the zone around our well. So essentially saying that the technology is working. We are making significant amounts of carbonate in that region surrounding the well, so that CO2 would be permanently stored. And again, this is showing, so injecting supercritical CO2, this is millions of tons. And so this is in the supercritical undissolved form, and then this is CO2 mineralized. And what you see is that these estimates really matter. You really have to do the hard work of characterizing the rocks that we're actually injecting the CO2 into in order to understand CO2 mineralization at the field scale. All that being said, we do see significant mineralization in these simulations, again, suggesting that CO2 will be prevented from ever interacting with the atmosphere and warming the planet. And so that's a good thing. So again, coming back to this, so to increase CO2 mineralization, perhaps we just need to inject less CO2, right? I don't want to be the one that tells Greta Thunberg that we can't inject more CO2 because of the alkalinity budget. So perhaps the light bulb here, and this is essentially my involvement with the Peach project, came whenever I was thinking very hard about this problem of alkalinity in basaltic aquifers. And Steve, I think, happened to be walking by my office and mentioned their ongoing work, or Peach's ongoing work in this realm. And so perhaps what we've been working on is maybe we just need to inject the CO2 differently, or change the aquifer alkalinity budget in order to make the CO2 mineralize faster. And so Peach, what we're doing as part of this project is working with smart electrochemists like VT and his research group to look at perhaps changing the alkalinity budget of seawater by manipulating the major ion chemistry. And so what we see here is the major ions in seawater. And as I think many of us might be frustrated by, so even though as Dr. Rao mentioned, the carbon content of the ocean is enormous, it's only enormous because there's so much water in the ocean. In fact, the carbon concentration of seawater per kilogram or per liter of seawater is less than that you might find in many groundwaters, for example. So there's actually not that much carbon in a single liter of seawater. And so what we are thinking about is, well, if you manipulate the chemistry, for example, of sodium or potassium or calcium or magnesium, as Dr. Rao mentioned, by just a little bit, then you can increase the carbon dioxide storage immensely, because it's essentially a charge balance equation. So if you are even not that good at manipulating the sodium concentration, let's say you manipulate it by a few percent, you can really get at doubling your carbon storage in seawater. So that's the premise of Peach, and that's what we're working on now. So closing thoughts, sorry, these are out of order, unfortunately. Subsea floor basalt offers enormous capacity for CO2 mineralization, but injecting CO2 at the rates required to hit the gigaton per year scale is going to lower the pH, increasing carbonate solubility and decreasing the efficiency of this reaction. Peach, and perhaps other electrochemical techniques that we're going to hear about today, may offer a way to improve on this by changing the alkalinity budget. And it shows to me that even if you're not that good at manipulating the alkalinity, you can really change the carbon balance of seawater. So thanks. I hope there's time for questions. If not, I'm happy to participate in the panel at the end of the session today.
Thanks very much, Ben. So we have a question from Kejuan, who asks, capturing the CO2 at the boat using DAC powered by wind energy, I think a major benefit is the location freedom, but is it actually better than CO2 transport by pipeline? Am I missing some other benefits?
Yeah, so that's an excellent question. And this is a sort of out of my personal expertise, but in the very smart people that I talk to, that I hope I can channel their thoughts here as well as I can. Essentially, the nice thing about being offshore, other than the one that you mentioned, is sort of the prime benefit, which is, you know, having location freedom. But the secondary benefit is that offshore wind, if you're able to exploit it, is not taking away from grid capacity of wind, right? So if we're able to use offshore wind that would not overburden or not add to the burden on renewable energy on onshore or near cities, wind energy or renewable energy, then we have a like a sort of limitless supply of wind that we might be able to use that then doesn't imperil the efforts to decarbonize land-based electricity generation. So that's the other major benefit that I can think of about being offshore. That being said, I think solid carbon in the basaltic aquifers they're permeable, they're porous, they have lots of space for CO2. So you might as well also consider actively taking CO2 in tankers or pipelines out to these reservoirs as well.
So there's lots of porosity there, but you're filling it up with carbonate. So Ali Abedini asks, how much is CO2, whoops, got to press the button here. How much is CO2 injectivity impacted by CO2 carbonation and mineralization, reducing permeability?
That's a great question. And so we've run lots of experiments on this. And even the CarbFix project in Iceland has been actively doing this at the field scale for a number of years. And the short answer is it seems like negligibly, at least over the scale that matters. So that we are making abundant carbonates, but we're also dissolving basalts, right? So I think that in the end, you do decrease porosity, and perhaps you create some dead end pores in these rocks, but they are extraordinarily permeable. They're more permeable than most conventional oil and gas reservoirs, for example. And they've got quite significant porosity as well. So I think the chances of really mineralizing to completion and to closing off porosity are really quite low.
Okay, thank you very much. In your reaction system, dissolution, carbonation, and so on, what are the rate limiting steps, and where are the knowledge deficits in terms of key things that researchers need to discover in order to kind of better describe the modeling and the feasibility of the process?
Yeah, so I think every one of them has its own significant uncertainties. I think that's the plight of the reactive transport modeler. But to me, we need to know better, or at least at some basic level, how relative permeability in these rocks works. So we're injecting CO2 into basalts. Nobody has ever really parameterized relative permeability of CO2 in water in basalts because it's not really been a priority of the oil and gas industry, who derives most of those parameters. So we really need some field scale verification of the parameters that we are using for those estimates. And then secondarily, this thing that we've really focused on, and I think is fundamentally important according to our simulations, is the mineral reactive surface area. So how do you actually characterize the rocks well enough so that you can produce predictions of dissolution rates that are going to be applicable at the field scale? And so I think that's our number one thing that we are personally tackling in our research.
So Dave Sinton's got his hand up. I think he'd like to ask a question. There he is.
Great. Thanks. Cool talk, Ben. I'm wondering if other offshore technologies give you a sense for the multiple in terms of the economics. So offshore oil rig versus onshore, is it 2x? Offshore wind turbine versus onshore, is that 2x? Is there sort of established technological multiple one should think about in terms of how much it's going to cost to move something offshore?
Yeah, And that's, I think you're actually working with our colleague Karen Crawford, who's really doing a lot of those, a lot of that work. He's part of the Solid Carbon Project, putting those numbers together. I can say it is substantial, right? Marinization of a lot of these technologies, particularly DAC, has substantial costs associated with it. And the thing that we're trying to evaluate is like, is it worth, because of the benefits, is it worth then still doing this offshore? And I think that that's the jury is still out on that. Those guys are working really hard on that project.
Thanks. So final question, Stuart Hazeldine asks, how do you verify the CO2 has mineralized rather than escaping as dissolved CO2 or leaking into the sea?
That, as Steve will also know, is the $1 million question, right? So I think as geophysicists might say, well, we can listen for things like mineralization actually happening, like the popping sound of carbonates being precipitated in pore space. We can try to do imaging of the plume. We can try to do sensing of the water column above the sediments in order to see if there's any increases or changes in the CO2 concentration in that water. But I will be the first to admit that that is the #1 smoking gun problem that we all need to work on in order to verify these technologies at the field scale.
Yeah, and I think we'll probably come back to these issues in general in the panel. So thanks very much, Ben.
Yep, thank you.
Yeah, with that, we've already heard about the importance of linking regulation and governance of these projects into the technology projects. So with that, I'll hand over to Anna Maria Hubert, who's going to talk about developing responsible governance in the marine CDR space.
Okay, so hello everyone from Calgary, and today I'll be offering a different perspective. I'm a legal scholar, but I'll also be discussing some of the social and justice dimensions of the development of marine CDR technologies. And so the first question, or starting point for this discussion, is why do we even need to look at governance? And so it's important to recall that even from the very early stages of this conversation, so the 2009 Royal Society report on geoengineering the climate was the start of the mainstreaming of this discussion, where CDR falls under this umbrella term of geoengineering. You can see that very early on, the governance conversation was integrated into how we think about these technologies and their development. And so you see this widely cited quote that the acceptability of these technologies will be determined as much by social, legal, and political issues as by scientific and technical factors, and that we have serious and complex governance issues to contemplate. And so lawyers and social scientists and humanities have been involved in this conversation from the outset. And so that's really important to know, because when we think about science and technology, it's not just about coming up with ideas to resolve certain problems, societal issues. So it's not just about developing the kit, proving that it works, and figuring out how to scale it up. But these technologies have to be implemented in society, and there are different forces and values and preferences that shape whether they can actually be employed downstream. And so now we're getting smarter about incorporating and asking questions about societal interests, legal issues, and so forth, upstream in the development process. And when we're talking about climate technologies in particular, and marine CDR, they have the potential to be quite disruptive and involve trade-offs. And so that's why it's important to make this a broader interdisciplinary conversation, but also to involve other societal stakeholders and even the lay public. I think the governance conversation can also be seen in terms of a time perspective. And so we can think about governance in terms of setting a vision for where we want to be. And often this vision is somewhat utopian or idealized. In light of what we've learned from the past. And so it's about building a roadmap for getting from where we are to where we want to be. And so in law, we have these two, we love our Latin terminology and maxims. We have this idea of lex lata, law as it is or as it currently stands. And then lex ferenda, sort of where we want to be in the future as normative analysis. And I think it's really important to sort of understand that there's not just one version of lex ferenda, but that this is subject to, this is obviously a contentious issue involving many different values and perspectives and so forth. And so marine CDR governance is, you'll see many different ideas about how it should be achieved. So normally then following this lex lata, lex ferenda idea is we look at first, what does the law require? So descriptively, how is marine CDR currently being regulated and governed? And we have sort of multiple levels at which we can ask this question. So what existing norms and also institutional processes are relevant to governance? And then can we do better? So sort of prescriptively creating new rules, taking into account legal, social justice and other considerations into account. How should marine CDR be governed? So what do we mean when we talk about governance? And here it's important to know that, and I am a legal scholar predominantly, that the sort of vision or understanding of the concept of governance is broader than just law and regulation. It's a comprehensive and inclusive concept. And here we have the version from the IPCC, which includes a range of means for deciding, managing, implementing, and monitoring measures. And it not only includes state actors, so government, and here we can think about different levels of government, but also various sort of subnational, local, and members of the private sector, civil society, and so forth. So it's a much broader concept than just law. And so when we think about the governance elements of CDR, there are ideas about upstream research and development, including financing, innovation, but also environmental ethics of in situ experiments, the role of law and governance in setting targets and distributing responsibilities for removals, impact assessment at both the project and strategic levels, property rights, liability, accounting and verification, monitoring, as well as public consultation and engagement. So that those are just some of the things that we think about when we're talking about governance of CDR. So again, we often start with the law as it is, lex lata, so the existing legal framework. And I'll walk you through that now. So really the work, we've sort of seen like versions of the world from a more scientific or technical perspective. When lawyers see the ocean, that's sort of one of my primary areas of research is the law of the sea. We superimpose our own structures onto the oceans and atmosphere in different spaces. And within these different structures, we have different legal concepts, so different rights and responsibilities of different actors within these particular areas. And so we are interested in sort of basic questions such as how can the marine CDR activity be characterized? What are its adverse effects? Who is undertaking the activity? Where is the activity taking place? And so forth. And so these are all really important questions. And so when you think about the sort of desirability of certain technologies over others, the legal analysis certainly weighs in to how we think about the possibilities for implementing these technologies. So, and I would say when you sort of, on the face of it, think about marine CDR, obviously we're mostly working in the water column or on the seafloor. And so it sort of makes sense to start with the law of the sea, and it is, I think, the controlling framework here. But we also know that other areas of law are really relevant, and obviously international climate law. And so the ocean atmosphere interface is really important, as well as other priorities such as the conservation of marine biodiversity. And so that falls under another set of rules under the 1992 UN Convention on Biological Diversity. We also have an interface between oceans and biodiversity, where there's a new treaty being negotiated under the auspices of the UN General Assembly on the conservation and sustainable use of marine biodiversity in areas beyond national jurisdiction. So areas beyond where any one single state has jurisdiction and control, and that would also be relevant to how we assess marine CDR, emerging marine CDR technologies. So I'll give you both an international law and also a Canadian perspective on the law. So Canada is party to the 1982 UN Convention on the Law of the Sea. So this convention predates the time when climate change was even perceived to be an issue. It was organized and negotiated in the 70s, but it's comprehensive in scope, and because it's also general and sort of meant to be providing overarching constitution-like framework, the provisions can be relevant, interpreted in the context of modern issues, such as climate change measures, and in particular marine CDR. And there are also mechanisms within the convention that allow for its elaboration to address new issues, including in relation to environmental protection. So we think about this convention as both setting out the jurisdictional frame in a spatial context, so starting from the coastline, or what we call it the normal baseline, or wherever it could also be a straight baseline, but starting from the coast, the coastal states' rights diminish moving seaward from that coastline. So the greatest freedoms would be on the high seas, and greatest coastal state control is near to the coast in the territorial sea. And so this is how we think about rights and responsibilities under the law of the sea, with the starting point for any kind of governance question, in my view, would be to ask, well, where do you want to do this? And then following up with how and so forth. The Law of the Sea Convention also regulates or allocates jurisdiction functionally, and a number of sort of areas of functional jurisdiction are relevant, including the protection and preservation of the marine environment in Part 12 of the Law of the Sea Convention, marine scientific research in Part 13, as well as transfer of technology in Part 14 of the convention. So here you just see a summary of the many different ways in which marine CDR may interact with different subject areas of the law. And this is Article 237, which allows countries to extend or create new legal regimes in relation to the protection and preservation of the marine environment, so long as they're consistent with the general principles and objectives of the convention. And so one example of this in the marine CDR space is the new regulation on marine geoengineering, which was adopted in 2013 under the London Convention, which regulates dumping at sea. And so I think this is the most specific legal instrument that we have in this space. So since 2007, the contracting parties to the London Convention, which regulates dumping at sea, and its more recent and precautionary London Protocol have been studying measures, first in relation to concerns of ocean fertilization activities in the ocean, so these biological methods, but also more broadly marine CDR, or marine geoengineering as it's called in the new amendment. And so we've seen a series of legally non-binding resolutions addressing ocean fertilization, and then culminating in the adoption of a new amendment to the London Protocol. And this was, from a Canadian perspective, partly precipitated by some unauthorized ocean fertilization activities that took place just beyond 200 nautical miles, so on the high seas, in relation to the Haida Salmon Restoration Corporation, but they originated in Canada, so communities in Haida Gwaii. And so that was a sort of Canadian part of the story of this new regulation. And so this new amendment was adopted in on the 18th of October, Friday the 18th. And so you can see here, after the adoption, we all took a photo. I was there as representative and advisor of the International Union for the Conservation of Nature. So I got to see how the sausage was made, but now we have the text itself. This new amendment is not yet in force, so it's only been ratified by, I believe, 6 states so far. And I meant to look this up, but I don't believe Canada has yet ratified this amendment. So it comes into force with 2/3 of the agreement of the parties to the London Protocol. So more ratifications are necessary for this to be binding. So we have this definition of marine geoengineering. Quite a broad definition, but this doesn't define what the scope of the regulation is. Basically, what we have is a sort of positive listing approach. So activities that fall within this broad definition of marine geoengineering, so deliberate intervention in the marine environment for manipulating ocean processes and with certain effects, deleterious effects, that captures a lot of different kinds of activities in the ocean. But basically the only marine geoengineering activities that are regulated are those that have been listed in a new Annex 4. And currently the only activity that is listed in Annex 4 is ocean fertilization. Those activities that are listed can either be subject to a permitting requirement or subject to an outright prohibition. But certainly this regulation allows for the inclusion of new kinds of techniques such as ocean alkalinity enhancement within the scope. But again, it's not enforced. There are also measures for conducting environmental impact assessment and expert advice in relation to that. So Canada is party to the more recent London Protocol. I don't believe we've ratified it yet. However, And we implement these obligations of international law under the Canadian Environmental Protection Act, or CEPA, Division 3, Part 7. And there's a sort of a tricky legal way in which we've actually incorporated the legally non-binding resolutions in the scope of that, or they're being interpreted as being within the scope of that. I won't get into the technicalities so much. The 1992 Convention on Biological Diversity, the conference to the parties have adopted a number of legally non-binding decisions in relation to ocean fertilization and climate geoengineering, again, which would include marine CDR, presumably. And so the most famous one is decision 1033 from 2010. But we see, for example, in more recent decisions, so they're a very sort of precautionary approach and outlining some of the governance requirements for these kinds of activities. So no implementation, only research, and requiring a precautionary approach and so forth. Sort of more recent decisions have called for greater research, transdisciplinary research. So not just science, but other disciplines, as well as engagement with societal stakeholders. This is how we think about transdisciplinary research. Obviously, climate law is also relevant. CDR is not explicitly addressed either in the 1992 Framework Convention on Climate Change or the more recent Paris Agreement, but it has been interpreted as falling within the mitigation provisions as a kind of sink. The Paris Agreement is sort of the framework we're working off of now, and it doesn't specify a number of key things that would be relevant to the governance of CDR, such as how to achieve, like, what is an appropriate balance between emissions, reductions, and removals. So Article 4 is relevant here. We also know that marine CDR as a kind of mitigation falls within this sort of bottom-up structure that has been adopted under Paris, where each country prepares their own sort of plans or nationally determined contributions for how they'll pursue domestic mitigation. And so nothing really in the convention now, at least, or in sort of further decisions. And the rule book precludes states from including CDR in their NDCs beyond sort of land-based reforestation and forestry methods. But currently, states aren't really including CDR in their NDCs. Okay, other mechanisms are also relevant, such as market mechanisms, transparency, and so forth. Unfortunately, I don't have tons of time here, so I'm going to move on. There's also customary international law where you have transboundary harm, and other areas that I think haven't been looked at, such as international human rights. So there's an international human right to science, so the right of everyone to participate and enjoy in the benefits of scientific progress and its applications. And it may be able to sort of link these broadly, almost universal human rights norms with, for example, governance demands for public participation and engagement, thinking about how we balance the freedom of scientific research with limitations and so forth. And there are also a number of soft law documents and principles that have been proposed. The domestic law situation in Canada is much like the international law situation. We have a sort of fragmented, sort of multi-level picture. So a number of different laws and regulations that address CDR broadly, but also marine CDR. But these are sort of disjointed, and the question is, like, how do we pull together all these different strands to have a more cohesive legal and policy regime? I'm sort of not an expert on the social dimensions per se, but I can sort of give you a bit of background. That's, I think, one of the really good sections of the National Academy's report on Ocean Cdr. And here, the conclusions have been that there isn't a lot of relevant social science research directly on marine CDR, and that the social dimensions and the justice dimensions of ocean CDR are much broader than this idea of mere acceptability, but need to be researched and supported if we're going to have a robust implementation of these approaches. And so you see here a number of conclusions related to the social particulars. Here, it's important to note that science and technology are embedded in social practices. And so, the risks and opportunities and benefits of marine CDR don't exist in the abstract, but are something that we should look in the context of how they're being implemented and used. Oops. Sorry. I have been I've been going over my classes, so I set my own alarm there. I was like, professor, class is over. All right, and so the way of sort of looking at the different social dimensions or study, one way is looking at analogs, for example, for, social research related to blue carbon, agriculture, and so forth. There are also a number of justice considerations regarding, for example, who should bear the benefits, but also the harms, risks and harms of the development of these policies. And this can be considered both on a time level. So do future generations have to bear the burden in implementing CDR? Should the West bear the burden as under the CBDR, common but differentiated responsibilities and respective capabilities principle? And also, for example, within a domestic context, we have issues of climate justice. So how do we distribute harms related to pollution in relation to removals and the benefits? So especially in relation to poor racialized communities. So a number of justice considerations here. So to conclude, the governance picture, like climate governance writ large, is fairly complex, involving multiple actors at different levels. And it's important to remember that this is a contested space. We all have different versions of the future of where we want to be, so what governance should look like, and the amount of governance we need. So there are significant uncertainties, different values and preferences, and obviously these are pretty high stakes questions in relation to the real threat of existential threat, really, of climate change. We have some regulations at the national and domestic levels, but it's not just an issue of filling gaps, but also the fragmentation of laws and governance, institutional processes, and so forth. So it's actually kind of a complex and overlapping space. And I think when we think about this question, I would really urge everyone to sort of cooperate and think about, how the kinds of research we need. And here I would say that we really do need a lot of different disciplines, as well as societal actors, including Indigenous peoples, local communities, environmental and other civil society groups, and even the lay public, to weigh in at an early stage in relation to the development of marine CDR. So thank you very much, and I'm happy to take questions. Sorry for going a bit over.
Okay, thanks very much, Anna Maria. So we have a question from Tim. Hello, Tim. Tim Kruger. And he asks, what is your estimate of a realistic timeline for OAE being permitted from a legal perspective?
You mean like permitted where and by whom, I guess is what I would ask. So are you asking about the London Protocol in particular?
I think maybe I think it's the question along that you talked about Lex Lata. I can't remember what your other legal term was. What other timescales we're looking at there? Are legal scholars aware there's a timescale issue and what's being done to accelerate things?
Yeah, so these issues have been studied sort of since the adoption of the Marine Geoengineering Amendment under the London Protocol. These issues have since been studied by various bodies. So GAZAMP did a big report, and they've been communicating with the London Protocol. There's like the National Academies reports about the domestic level, the GGR report by the Royal Society. And so I think, so we've been studying these issues, but sort of what will precipitate actual sort of governance or regulation is what has prompted it in the past is field experiments in relation to ocean fertilizing, like sort of real conduct where we think, well, we should probably do something to make sure that this is done in a controlled or way or with oversight. So I don't see any indication that it will be regulated, but it's certainly being or governed specifically, but we see this being studied and it's seen as a key part of moving forward. So timelines, next 5 years. I don't know.
Okay. Okay. So you've been one of the pioneers, both Calgary and internationally, in bringing governance, legal thoughts and concepts into the sort of geoengineering CDR space. What are the barriers and how do we overcome them in terms of, if you look at like conservative institutions like universities, how do we improve this mix of disciplines and concepts and expertise?
Yeah, I mean, I would say that like in many ways, and I guess I sort of cut my teeth in this area, so it's sort of in some ways my only like real practical experience with how we like think about governance of emerging technologies. I've since sort of looked at other areas, but and so in some ways I think it's sort of been like a good model for how you do it from the start. So we've always thought in terms of interdisciplinarity in this field. But there are those who think, for example, why would we involve like the rest of society in these decisions? We don't have time for this. That'll just arm like environmental groups who are opposed to these kinds of measures. So there is a pushback in terms of the question of who should be involved in these conversations. So there are those who sort of favor a very sort of narrow technical and scientific framing of these questions and sort of want to keep the lawyers and everyone else out. I don't blame them for wanting to keep lawyers out, but there might be good reasons to have us there. Finance for we're like really getting moving on the science and testing of these projects has been an issue, I think, for a long time, but that seems to be shifting a bit. What else?
Okay,
yeah.
Thank you.
I mean, like, I guess the question is, like, the barrier is sort of determined in terms of how good do you think it ought to be? So some people would say lack of sort of real binding rules in relation to field experiments isn't a problem. We do these kinds of things all the time. But others might say, well, can we do it better? So it's a values judgment to some extent.
Yeah, thank you. And I'm sure we'll come back to some of these areas in the panel discussion. So I've got on my clock here, 10:44 local time here. Let's take a 5-minute break. So 5 and a bit, we'll reconvene at what for me will be 10:50. So 10 minutes to the hour, and then we'll continue with Dave Sinton and Matt. So quick 5-minute break. Okay. I think we're about ready to resume. And if Dave's there, and he is, fantastic. So we're going to continue with looking at electrochemical CO2 manipulation. And Dave is going to give a talk on developing electrochemical routes to CO2 capture and conversion. Over to you, Dave.
Great, thanks, Steve. It's a pleasure to be here. Great talks this morning and stimulating. How did I get here? I currently work at the University of Toronto, but that was not my first academic stop. My first stop was University of Victoria, and we've already heard from Ben here and others with connections to UVic. And it was really there that I got interested in energy systems. I was a microfluidics guy, a transport guy, and working on electrochemical fuel cell type things. And it was in 2009 when I pitched Steve Larder and others on a project for CMC, where we'd use these types of methods and look for opportunities to understand how CO2 moves in the subsurface. And that produced some great work. And a little example up on the top there with a chip. This is a small fluid system, a model of the subsurface, and you've got these little channels in there.
So I can't see your slides, Dave. I don't know if others can see them or.
Sorry.
That's all right.
Yeah, same thing. I cannot see.
Well, that's on you guys. Sorry about that. How's this? This is better.
Yes.
That looks better. Yeah.
Okay. Yeah, the audio is great, but there really is some visual content here. So that's great. Yeah, so rewinding 10 seconds there. UVic, that was electrochemical, introduction to electrochemical systems, fuel cells at that time. The West Coast was a hotbed for that stuff. And then fast forwarding a bit, carbon management Canada, taking a bet on this technology for understanding CO2 in the subsurface. And so here was an example. We had CO2 flowing in these little channels, and then we had some salt formation. Lots of talks today about salt formation and CO2 in the subsurface. Here, this is salt formation with CO2 moving into a saline solution, and then we can do some cool microscopy and track even the acidification of the brine. We couldn't get find a commercial buyer for that technology. Couldn't make a business case specifically on CO2 sequestration at that time, but we did find interest in industry for these methods and how they can inform fluids in the subsurface to make operations more efficient. So chemical injection into oil reservoirs, and that's and additives and steam and solvents and all sorts of oil field technologies, making those more efficient, more chemical efficient. That's been a success of Interface Fluidics, a company based in Calgary and at labs in Edmonton. And then more recently in Calgary, we've been working on the Carbon X Prize. I'm going to share a slide on that today. I guess I'm making the case here for Alberta citizenship or honorary citizenship or something. But lots of connections here across the country and a history of transport and electrochemical systems that bring us to our current project. If we look at the historical view of world energy, I used to describe this plot as how energy sources, how we replace energy sources over time, and how better energy sources take over from not as good ones. But that description is not correct, because really we don't replace them until we add, right? So we add new sources. That's what we do. And something not captured here is that we add efficiencies. So lots of we're squeezing more value out of the energy we take. We're good at that. We have a historical track record of that. What do we not do? We don't subtract, right? We don't subtract well. We have no history of doing that in terms of our energy usage. So when we add all that up, I think the main conclusion for me is that demand will persist. Demand for these energy forms will persist, and CO2 will persist. And of course, this audience, it's not hard to convince that we need to do something other than emit it into the atmosphere. Our approach has been to look at those CO2 emissions, both from the dispersed sources, so the air, and then also from industrial operations, and convert those electrochemically to chemical feedstocks and to fuels. We think of this in terms of the upstream is the CO2 source coming into the electrolyzer, and then inside, using what I think of as really our only silver bullet and the energy side, which is renewable electricity. This is high value stuff in the sense that it's very useful and can come with low associated carbon. So that energy and carbon efficiency, I'm going to tell a story about that. And then also on the downstream, what are we making? In this case, a story about ethylene, which is the world's most produced organic material, and then ethanol as a direct fuel drop-in. Over the last 5 years, been fortunate to work with the Sargent group at U of T and Kibria, who's organizing, co-organizing this session today, was involved in lots of this stuff back a few years ago, and we've really evolved through that time in terms of size and impact. So early on, what we knew was small scale science, small scale systems, and we've graduated over the years to electrodes, and then to systems, and then to bigger systems, actually pilot plants, and in terms of the technology, progressed a bit from pure CO2 to looking to other sources, and then now an effort on air as an upstream. So I'm just going to focus on the last 2 years with some examples. As I mentioned, I split the challenges in this area up into 3 areas. And on the input side, I'm going to give one example of where we're looking to try to use something cheaper than pure CO2. Flue gas would seem a perfect input. There's lots of flue gas around. Certainly some flue gases are more interesting than others. When you're talking about electrocatalytic technology, flue gas from a coal plant is not that attractive because ultimately you need low carbon electricity here. But flue gas from persistent sources, and there will be lots of them. Think about steel or cement processes. That flue gas is fairly concentrated CO2, and it can be very cheap compared to pure CO2. There's lots of challenging parts in that, and we've got a few projects going on and trying to attack those challenging parts, the NOx and the SOx. This is a very first effort and just dealing with the oxygen in those systems. Oxygen isn't poisonous, but it doesn't poison the catalyst, but it does derail the whole process. So if you have a system that's designed for pure CO2 reduction and you introduce oxygen, the oxygen just takes over. So you do oxygen reduction and you don't do any of the CO2 reduction that you wanted to do. So we did some engineering, again, leaning on our small scale transport background, and developed these nanopores that use the property of CO2 solubility in water being higher than that of oxygen, and really allowing CO2 to beat oxygen to the surface. And we could regain our Faradaic efficiency. So this is just the selectivity with which we make what we want to make. In this case, C2 products, mostly ethylene, being produced from CO2. I'll tell a story on the cell side in terms of productivity, efficiency, and stability. Those are all things we need if the technology is going to be viable. So this work was really maximizing on one metric, and that was current density. So if you think about a technology like an electrolyzer, it needs to be above a certain current density, a certain productivity per area, in order for the capital cost to be reasonable. If it's too low, you just have to build too many electrolyzers to have a reasonable throughput, and it's not viable. There's lots of discussion on what's the right current density, but certainly 1 amp per centimeter squared is in line with other electrocatalytic tech, and is considered more than enough for viability. But previously, electrolyzers weren't anywhere near that state. So this one solved that really with transport, and we brought everything together at this interface, and we extended the transport of a gas along the catalyst. And that was just a little trick here with a surface coating on that catalyst. So the trick was to get the gas through along the catalyst, have it stretch, and really increase the active area effectively, and get to large currents. And the challenge with this is really reflected here. What was happening when we didn't do this? We had really fast loss of CO2 into that alkaline solution. So alkaline conditions are favorable for producing C2 products. We need that, but we lose tons of CO2 to carbonate. That's off target for us, and it's very expensive. So great current density, all sorts of other problems. When you look at the techno-economics for this, and after we published that and others related works, there was a couple very good TEAs that came out and said, you guys are crazy. No one's ever going to do this because your cost to regenerate and get that CO2 out of your electrolyte is way too high. Point taken. We had to find a way to keep CO2 from moving into carbonates in this case. Our approach to doing that was separating the process. So CO2 to CO in a solid oxide cell. So this is, you can go down to IKEA and buy one of these. Well, maybe not IKEA, but they're an off-the-shelf unit. They're high TRL, and they produce CO, and this gets around the CO2 going into carbonate on us. So we get a fairly low energy cost CO that then we can then convert to ethylene. So it was a two-step process. And we got an overall energy basis to about 140 gigajoules per ton of ethylene. And for those of you who don't spend every day thinking about the lower heating value of ethylene, it's around 50 gigajoules per ton. So we're spending 140 in electrical energy to get to something that's 50. We're at least getting there. We've added a fancy anode to this side to this system to try to pull those energy costs down further. In conventional systems, you're just doing oxygen evolution at the anode, and it's expensive, and you don't sell the oxygen, so you just got to do it. But there's no product there, and it costs a lot. So we developed an anode that we think could pay for itself in terms of turning glycerol coming from biodiesel processes. Can be quite cheap, and then producing C3 products that are at least as valuable as that input glycerol. And if it could manage to just pay for itself, we could get the ethylene business side of the cell down to pretty compelling levels in terms of energy input per ton. So these system, admittedly, we've done lots of tricks here to try to get our energy input down for our product out. We looked at there's a simpler way to do this, not in a tandem system and not with a glycerol eating anode, but back to basics. And we recently developed this permeable CO2 regeneration layer. So here again, instead of we still have CO2 converting to off-target carbonate ions and carbonate, but we recycle it locally. So we're able to have locally acidic conditions. So the CO2 is regenerated locally, and as a result, we can get to single pass conversion efficiencies of 85%. And back a few slides when I was saying how the field was really calling for, that's a nice way to put it, for a solution to this carbonate problem, for CO2 to C2 products, the maximum was 25%. That's a fundamental maximum with conventional systems. So getting to 85 was at least addressing that barrier. Great. One last story on the output side. So here, we're really focused on, can we make a product that's valuable, that's high purity? Us and the rest of the field are guilty of making a product, and we measure it, and we don't fib about that. We report our ferritic efficiencies. We made some ethanol maybe. So we accurately measure it. But if you were to say, well, what's that solution worth that you made it in? The answer is not much. This is the ethanol plant of a industry partner, Suncor Energy. This is based in St. Clair, Ontario. And these guys make 400 million liters a year of ethanol by a conventional process, and they've got a CO2 source here clearly, and they've got a downstream market for the ethanol. So there's lots of interest in, can we have a parallel process that's actually electrocatalytic? But the challenge is they need 10 weight percent ethanol in these systems, and every work in the field to date before our efforts were sub 1% in terms of the actual concentration of what came out of there. And if you tell our Suncor friends that we've got a 1%, 1 weight percent solution for you of ethanol, they'll tell you, well, you've got a waste problem. You don't have a value stream. What was the challenge there? Well, we'd make the ethanol with conventional systems, but then it would go across the membrane. Ethanol is very wetting, loves membranes. Membranes don't like ethanol, but ethanol will go everywhere, and it can even oxidize on the anode. So it was hard to trap ethanol and keep it where we wanted it. So we developed this system. This uses a solid state electrolyte here in the middle, and it uses some ion flows that are strategic. They keep the electroosmotic flow all flowing into the center, and it keeps that ethanol trapped. And as a result, we're able to produce some pretty high concentration ethanol here, getting up to 15% or 14%. And that's a Merlot or something. Most importantly, it's maybe the first ethanol solution ever produced by CO2R that's been valuable. It's actually been worth something, as opposed to being waste. Great. I talked about scale up. This is just one slide showing our effort on, this was really the Carbon X Prize effort, multi-year group of dedicated students from my group and Ted Sargent's group. And I think even Kibria was involved in early years on this. And it was really a great opportunity. X Prize really gives you the opportunity to go for something big. And I'm happy to chat about this if there's questions. I think this is still the biggest CO2 electrolyzer in the world. Last stop, where to from here? I'm really interested, and I know there's interest in the audience, on the ultimate upstream. I guess I should have two ultimate upstreams. One is ocean, CO2 in the ocean, carbon in the ocean, and the other one we've been active on, which is CO2 in the air, so 400 ppm. In that case, we're working on, we haven't learned our lesson, and we're doing another X Prize effort here. And the top part of this diagram is the air contactor. And here we're saying people have developed this. David Keith and friends at Carbon Engineering have done a great job. This is an established tech. Where we want to help is in this regeneration part. So currently the way you get your CO2 out of your capture fluid is through a largely thermal process, and that has associated emissions. You can still come out ahead on that, of course, but it's a shame to be producing those emissions as part of your CO2 direct air capture. So having low carbon electricity do the work is the approach here. And this is an electrochemical system that pulls on all the tricks I mentioned earlier. And this is a young team, and they've got these guys in my lab in Toronto here, and they got some recent support, early bit of funding from this competition, and they have enough money to fight another day here. You'll see. Great. With that, I want to thank the people who do the work, of course, is the team, and we're very fortunate to work with Ted Sargent's group and funding sources, and most importantly, thank you for the invitation for this symposium today.
Thanks very much, Dave. So let's look in the questions here. So, you know, you're looking a lot at solving these transport problems, essentially, in a general sense, in these electrochemical devices.
Right.
So they're becoming more complex. I mean, any insights on the durability of these more complex systems?
Yeah, it's a good question. Where are we at? The fields, you need to be around, even if your story is a new catalyst, you've got to be around, 10 hours or something before you'll be taken seriously. I think that's rapidly increasing to 100 hours. Where do we need to be for commercial viability? As folks in the audience would know better than me, but I think the number is 10,000. We've had cells that'll go 500. As part of the X Prize effort, we were getting up into the hundreds of hours. So that's a major push. One, you mentioned the complexity there. Some of the other challenges, like the carbonate problem I mentioned, I said it was terrible from an energy perspective, which is true. It was also terrible from a stability perspective because those salts make a mess of your system. So sometimes solving those problems has resulted in extending stability as well. We've got another 10x to go before we can really be taken seriously.
Okay, thanks. Yeah, VT gets excited about this kind of stuff, and he's got his hand up there. So VT.
Right.
All right. So Dave, it's a nice talk. Thanks for updating on the status. Given the both of this SOEC and then the one with the oxide analog versus the proton analog, which one is the most favorable for scaling up opportunities you see as an electrolysis product here?
Yeah, well, the SOEC, that one, it will get you to CO. So that's the end of that story. But we love that because it's well established, and then we can go from CO to the products that we're more interested in. I think that's really the competition. There's sometimes I'm told that the SOEC isn't as established as I want it to be, but I think they're at least further along than we are in that step.
Okay, thank you.
Thanks. So a question from an anonymous attendee. What application route for this technology do you see in marine CDR?
Yeah, it's a good question. I've been thinking about that all morning here. I mean, one challenge is the concentration of CO2 or carbon in the ocean isn't high, so you have to move a lot of water. But I think thinking about the talks today have inspired me to think a bit about ocean changing ocean pH as a goal in itself. And maybe you think of integrated systems that could where that could be part of the value stream. I think that's interesting for sure. Yeah, no, I would say I'm inspired, but we haven't looked into it significantly.
Yeah, I think one of the takeaways I got from your talk was that these overall systems are going to be very complex, right? And yet one of the last applications you talked about was taking a carbon engineering type CO2 stream and just improving the processing of the carbonate there, right? That could be a very pivotal gain in terms of like a marine DAC system and things like that. So perhaps as academics, we tend to look as though we're going to solve the complete problem, whereas actually maybe we're just going to provide a key component to a much bigger enterprise.
Right. Yeah. Great point. Yeah.
Yeah. Gabriel.
Thanks, Steve, and nice to see you, Dave, here. And so my question is related to the scale, especially when we work in the lab. The electrolyzers are pretty small, right? So the challenges we face in the lab, and you mentioned about the X Prize and the scale up and the largest system you have demonstrated. So I guess the challenges you faced when you go to the larger scale is probably a bit different from what we see or we do not see in the lab. So what are the key lessons or key takeaways you had from the X Prize scale up system?
Yeah, good question. I can give you a few. You know, one is you got to scale up to learn these things, right? And it's not the last lesson in terms of scaling CO2. A few obvious, well, I shouldn't say obvious now that we've done it. In plane currents, in plane gradients really start to hurt. So that's the bad news, right? And gradients in everything. So you've got now significant amount of ohmic loss in plane. You've got concentration gradients in plane. You've got product gradients in place. So that once your cells get large, because they have to, you start to have these sort of familiar to chemical reactor problems, right? So those present. The flatness of the cell, the compression is hard to get right at large scales. It's not impossible, it's just challenging. Other things, other really surprising things, you've got a big tank of electrolyte and it's hot. You're on the Canadian outside of Calgary in the summer, and your big tank of electrolyte can grow some green stuff, right? So you're producing bio products, I guess, but you're also making a real mess of your system. So that's an example. It's kind of funny in a way, but it's not funny when you're there and you've got a huge tank that's got a biofilm problem, and you've pushed that through your system. So those are the kinds of things that need to get sorted out when you scale.
Yeah.
Thanks very much. Thanks. Yeah. Okay, thanks very much, Dave. And we'll move on to another electrochemical presentation. And this is by Matt Eiserman, and he's going to talk about electrochemical ocean alkalinity enhancement for ocean acidification mitigation and carbon dioxide removal. So over to you, Matt.
Thanks a lot, Steve, and thank you very much for the invitation. It's been great listening to the talks up until now. Let's put this into slideshow mode. Great. Yeah, thanks again for the invitation. It's been a great morning of talks, I think all interrelated technologies and approaches. So as Steve mentioned earlier, I'm a professor at Stony Brook University. I'm also co-founder and CTO of EbCarbon. EbCarbon is a company formed by myself and my co-founders recently to commercialize the technologies I'll talk about today. And as the title says, we're doing electrochemical ocean alkalinity enhancement for carbon dioxide removal, but also a major co-benefit is mitigation of ocean acidification. So first, just a huge thank you to the great team of students and postdocs at Stony Brook University and my group, and collaborators, Brendan Carter at the University of Washington, the great team at NOAA PMEL, Hongji Wang, who was at NOAA and now at University of Rhode Island, and Pete Saris's group at Penn, and a super team of advisors provided by Ocean Visions, and then the team at EbCarbon as well, and funding from the Grantham Foundation for the Protection of the Environment. So thinking about the ocean acidification piece of it actually first, if you think about an oil spill and what happens after oil spills is we clean up after them, right? And really you could view the acidification of the oceans because of CO2 emissions as a slow motion acid spill, right? So we're spilling CO2 into the air. More dissolved CO2 gas is equilibrating into the surface ocean, and that is creating acidic conditions. And as others have mentioned today, actually, the ocean has done us a favor so far in terms of atmospheric CO2 concentration because it's absorbed something like 30% of human CO2 emissions. But that help comes at a cost, which is making the oceans more acidic. So the approach we're taking in the project at Stony Brook University is what we call CMATES. That stands for the safe elevation of alkalinity for the mitigation of acidification through electrochemistry. And this approach is the same one being commercialized by EbCarbon. So the science and research aspects are done at the university and commercialization at EbCarbon. At a very high level, shown here, what we're doing is taking seawater or any existing brine waste stream. So that's really ideal for us. For example, a desalination plant or a power plant that is already putting some brine effluent into the ocean. And we just take that effluent and process it first before it goes to the ocean. So it's an electrochemical system. I'll get into it a bit. It's electrodialysis, so a series of ion selective membranes powered by low carbon electricity that takes the salt in the seawater and separates it into its constituent acid and base. So hydrochloric acid, it stays on land and is used for beneficial purposes. I'll talk more about that later, but lots of overlap from some of the talks we've already heard about today. And then the remaining base, the base is mixed and diluted with the remaining seawater such that when we return it into the ocean, the pH at the dispersal site does not go above pH of about 8.5. So we'll have sensors at the point of dispersal, just monitoring that seawater chemistry, making sure that the pH doesn't exceed safe bounds for marine life and permitting. And so that sensor system is basically feedback to the electrochemical system. We can ramp the current and the alkalinity generation up and down fairly quickly in this system. A bit more detail, what's happening when we return this alkalinity or this base sodium hydroxide to the ocean, two reactions, one that effectively happens immediately and then one that takes on the order of months. So the immediate reaction is that hydroxide raises the pH of the local ocean, converts bicarbonate, HCO3- to carbonate, right? So there's a clear ocean acidification mitigation piece here, but then over months, as the CO2 in the air equilibrates with that added alkalinity in the surface ocean, atmospheric carbon dioxide reacts with that carbonate to produce an additional bicarbonate. So the net reaction is hydroxide plus CO2 is stored as bicarbonate. The ocean acidification piece comes from the fact that even after equilibration, so after this has fully equilibrated, just because of the equilibrium constants of the carbonate buffer system, not all of that carbonate is converted back to bicarbonate. So you get about 0.8 moles of CO2 drawdown per mole of hydroxide returned to the ocean. What that means is the pH doesn't return all the way. So, we add the alkalinity, pH goes up to something like 8.5 or so. As the CO2 is being drawn in and reacting with the carbonate, that 8.5 pH starts creeping down, but it doesn't go all the way back to where it started. So even after equilibration, there's some net ocean acidification benefit. One good question we get a lot is, wait a minute, you just told me CO2, the ocean's absorbing CO2 causes acidification, and then you told me you're solving it by making the oceans absorb more CO2. So just briefly, without this process, it's an equilibration, a Henry's law equilibration between the air and dissolved CO2 in the surface ocean, and that results in the release of hydrogen ions and ocean acidification. With the added alkalinity of the CMATE approach, that CO2 now reacts with the alkalinity to be stored as bicarbonate, which is the primary storage mechanism for carbon in the oceans. So just thinking about the metrics for carbon removal that some of the buyers of carbon removal in the voluntary carbon market are talking about, like Stripe and Microsoft, additionality. So would this have happened if we hadn't built this system and performed it? So it's 100% additional. That much is clear. The permanence is really quite good. This is essentially the lifetime of excess alkalinity in the ocean. And that lifetime is at least 10,000 years. We have a pathway to less than $100 per ton within 5 years. The scale, when I say greater than 20 gigatons of CO2 per year, that's if we say what are the limits just of the ocean system. So the ocean itself, the physics of this process, we can get into the many tens of gigatons of CO2 per year. And then separately, we've looked at constraints like electricity needs, membrane needs, acid offtake, and so on. And those also allow us, those constraints still allow us to get into the many gigatons of CO2 per year scale. Some people have talked already today about measurement, reporting, and verification. So one nice thing is on this system, we have conductivity sensors and pH sensors. We're directly measuring the rate of alkalinity generation. And then the sensors at the point of dispersal were directly monitoring the change in pH and other seawater chemistry parameters from putting that known quantity of alkalinity into the ocean. And then the third piece is regional ocean modeling. And I'll share some of that work from our partners on the modeling aspect, modeling how that alkalinity will spread and equilibrate over time. I'll show you in a moment that we're packaging this in a modular shipping container form factor. And so in terms of equity, it just allows us to be very modular in terms of siting and reduce local impacts. It's safe for marine life, probably beneficial. We're confirming that with mesocosm studies with partners because we keep that pH change, maximum pH change at the point of dispersal within safe bounds. And then I've already talked about the ocean acidification mitigation co-benefit. I think Greg already showed a version of this. This is gigatons of carbon, so multiplied by 3.7 to get CO2, stored in different aspects of the Earth system. And clearly what we're doing, and I mentioned that what we're storing the CO2 as is oceanic bicarbonate. You can see from the total carbon stored in the ocean that even at the multi-gigaton CO2 per year storage rate, fractionally, the oceans can absorb this additional carbon as dissolved inorganic carbon. And as others have mentioned, right, if we did nothing, the carbonate silicate cycle is the natural regulatory mechanism for regulating CO2 concentrations in the atmosphere. So if we did nothing over geological timescales, CO2 would be reduced in the atmosphere by weathering and storage of that CO2 as bicarbonate in the ocean. We're just trying to accelerate that natural process. So just thinking about the different aspects of the CMATE project, and I'll pick a few of these that I have time to go into today, and we can talk about others maybe in the questions if you want. The first, optimizing electrochemistry. This is really just driving, as I'll mention, it's driving the energy consumption down by thinking carefully about the membranes, the flow architectures, and the chemistry in the electrochemical system. Quantifying the chemistry, we're doing tank tests, and we'll also do a field test of the system to verify what are the kinetics of that slower CO2 removal reaction, and making sure actually that we know what the thresholds are for precipitation. We want to avoid precipitating calcium carbonate because that itself releases CO2. Performing techno-economic and life cycle analysis that actually drives our decisions about what to optimize in the system. And then process optimization for co-location with either existing industries like desalination or power plant cooling or others, aquaculture, or other CDR methods. So, I mentioned we generate dilute hydrochloric acid in the short term. So this is effectively a low carbon footprint acid, right? So typical standard acid that you would purchase industrially has some carbon footprint. Ours has zero carbon footprint, but beyond that, in our techno-economics, we assume zero revenue from selling the acid, which means that we will be able to sell basically green hydrochloric acid at a very, very low price. Because of that, in the near term, we're looking at just selling for existing uses, but in the medium to long term, we're identifying sort of new markets and uses for that that can get us to the megaton and gigaton scale. And a couple of those were already mentioned today, and they're actually sort of co-location with other CDR methods. So one possibility is to speed up kinetics of CO2 mineralization in basalt, or to extract valuable resources out of existing mine tailings. So that's a project we're working on with the Saris group at Penn. So there are a lot of overlap with these methods, and it's not surprising, right? Because in some sense, all of these approaches, we're all trying to accelerate this natural process. But if we're dealing with the ocean piece of it, it's not surprising that we often come back to mineral aspects of it as well. Modeling, I mentioned, is an important part of measurement and verification. So we're doing that with our partners at NOAA PMEL. And then setting up some mesocosm experiments to really demonstrate the safety for marine life, which is important for the social license aspects I mentioned. So briefly on how the techno-economics kind of drive, we're using the techno-economics to identify what are the sensitive levers that we should focus on the electrochemistry. So this is just a sensitivity diagram of the variation in the dollar per ton of CO2 as a function of how much we vary these different variables. What you see are two are the most important. So electricity, the electricity price, or the electricity demand in megawatt hours per ton of CO2, and the capacity factor. So actually, we assume that we will be running our system at 50% capacity factor. What that allows us to do, so we're able to turn the system on and off fairly quickly, but that low capacity factor allows us to selectively obtain low cost, low carbon footprint electricity now, not in the future. And ultimately will actually enable the build out of additional renewables by having a system with these low capacity factors. So all the economic projections, including less than $100 per ton, assume these low capacity factors. So it's clear we want to focus on reducing our electricity demand per ton of CO2. And the other reason we want to do that is that all of the costs I'm talking about are dollars per ton of net captured CO2, where we take, so in this example, I'm assuming this system in a shipping container has a capacity of something like 300 tons of CO2 per year capture, but we have to account for the electricity input and then assume what the emissions intensity of our input electricity is and figure out the emitted CO2 and subtract that off, right? And so in this example, 1.7 megawatt hours per ton, measured on our commercial system. Now we're at 1.9. We have specific steps that we're quite confident we can get to 1.5 megawatt hours per ton relatively soon. And then the question is, if we, for example, here are two examples. If we plug into the grid in the Pacific Northwest, there's a fair amount of hydro there. Then we're going to emit about 12% of what we capture. If we have pure wind electricity, which our capacity factor helps us get at low cost now, we're only emitting 2% of what we capture. And this is just the electricity emissions. That is the dominant source of emissions for us. So that's why I'm talking about that mostly. So this is why our main focus on the engineering side and the science side of the electrochemistry is to minimize that electricity use. As part of the CMATE project, we'll have a field test in the ground by the end of the year in a standard shipping container. The first one will be 25 tons of CO2 per year capacity, but eventually the ebb carbon systems will be 200 tons per year in that same footprint. So what we're using to perform this process is electrodialysis. I've shown at a very high level here, where we pre-treat seawater. We want to remove, well, it's either seawater or reverse osmosis concentrate or whatever brine effluent we're getting. Pre-treat it to get the divalents, the calcium and the magnesium to an acceptable level. Those will go back in the ocean later, but we take it out just for the process. And then, so what we're really feeding in is seawater minus calcium and magnesium, or reverse osmosis concentrate minus those calcium and magnesium ions, but I write it here as NaCl. And so we have this cell triplet, cation, bipolar, anion. The cation and anion just pass positive and negative charges. The bipolar basically enhances dissociation of water at the junction, and so creates acid on one side and base on the other under an applied voltage. The result is that salt is converted into an acid and a base. This is a picture of the CMATE field test unit that will be in the ground somewhere by the end of the year. And so this is in the form factor of a shipping container, and you can see these totes are basically just the fluid, acid, base, and brine input and output, and the electrochemical unit is in this this part on the right. So if I switch views, here you see the electrochemical unit, the electrodialysis unit. It's 0.5 meter by 0.5 meter cross-sectional area, and it has 50 of those cell triplets. And if you look on the end, you can see this kind of stack of membranes doing the ion transport. So this is basically a commercial off-the-shelf system, but as I mentioned, we have some specific improvements that we think can get our energy consumption down that we'll be implementing over the next year or so. Another important part of the CMATE project is to quantify the chemistry first, just to verify it, right? So these equations that I showed you, just to verify that by carefully monitoring the process in a controlled environment, that the chemistry is what we expect. Importantly, what are the kinetics of the CO2 removal, that slower reaction, and then also establish calcium carbonate precipitation threshold so that we, in practice in the field, know the rate at which we can add alkalinity and avoid precipitation. So this is the setup at Flax Pond Marine Lab here at Stony Brook. We have two 4,000 liter tanks. One's a control to which we'll do nothing. One is an experiment tank to which we will add alkalinity. On this map, Stony Brook University is down here at the bottom. It's where I'm talking from now. And the Marine Lab just a little bit away up on Long Island Sound. So this is Long Island Sound, Connecticut's to the north. And this little pond here is Flax Pond. And so we're taking water from that into the tanks for this experiment. So these tanks are fully instrumented with multiple pH sensors, oxygen, temperature, salinity. We'll be doing total alkalinity sampling, all of this in collaboration with our partners at NOAA at University of Washington. And I should say, these experiments are just starting now, and so we should have data within the month, I would say. And then an important piece is the modeling, especially when we get to the measurement and verification. So this is work with our collaborators at University of Washington and NOAA, and Hongji Wang, who is the lead author on this paper we just submitted, has gone from NOAA to University of Rhode Island. So this movie is showing, you can see here at Unimak Pass in Alaska in the Bering Sea, we assume basically a 0.5 megaton of CO2 per year size alkalinity dispersal system. And you're looking at two movies. On the left is the total alkalinity increase or difference due to this addition. And on the right is the dissolved inorganic carbon increase because of this addition, both in micromoles per kilogram, and it's a 10-year time loop that you're looking at. And so on the left, this is really the immediate reaction that we were talking about, the OA mitigation aspect. And so that's why you see this sort of brightly colored plume focused on the point of dispersal. And then on the right, the dissolved inorganic carbon, that equilibration takes a longer time. So as this alkalinity is spreading out in the ocean, the carbon dioxide is equilibrating. And so the end result is you see this DIC is pretty evenly spread out in the Bering Sea. And importantly, one important aspect of this from a measurement verification point of view is that the alkalinity stays in the surface ocean in this region much longer than the time it takes for equilibration. So here the full equilibration is about 3.5 months. The E-folding time's like 5 weeks, which is important because you don't want the alkalinity to be pulled to the deep ocean before it has time to equilibrate. We can also look at the OA mitigation aspect. This is for perspective, just looking at how much has ocean pH decreased since pre-industrial times. So about 0.05 to 0.15 units, and up in the region we're looking at, it's on the high end of 0.15, and that's to set the scale. So this is a result of the simulations looking at the spatial area around the dispersal point where the pH changed by blue, very small amounts, up to yellow, 0.02, and that yellow 0.02 value is meaningful, right? So we're making a dent in the ocean acidification on the plot I just showed you of 0.15. And so you see that kind of substantial mitigation of acidification happens here over something like 1,000 square kilometers. This variation is seasonal variation from summer to winter, as basically you're adding the total alkalinity and then it periodically gets kind of swept and advected away from the addition site. Finally, what I've talked about today were a lot of the research questions and science questions that we're pursuing at Stony Brook University under the CMATE project. And at the same time, where Ebb Carbon is commercializing this process, the same one I talked about today. So we closed our seed round in November. Stripe is our first customer that we signed in December. And so a lot of our effort is really delivering on our commitment to them right now. we're a competitor in the X Prize carbon removal, and we're one of 6 companies that were selected for the Ocean Vision's launchpad as part of that. And we're 6 employees now, but we're really growing quickly. So please, if you know anyone in this field, mechanical engineers, electrochemists, ocean chemists, oceanographers, and so on, have them send us their resumes. So we're looking for great people. And with that, I will take questions. Thanks for your attention.
Yeah, that was a great great finale. So I've got several questions in the thing, and looking at the time, I'm going to combine a couple into. So I'm going to combine a question from Yegos Radovic, who's part of our Peach team, and Richard Dewey, and they're both talking about HCl and chloride. And part of the question is, you know, to really scale the carbon removal, you're going to produce a lot of hydrochloric acid. Where's the market for that? And the other part is, how do you keep that chloride out of the ocean forever?
Yeah, great question. So this is something we've looked a lot at to make sure that this doesn't constrain growth to gigaton scale. So I tried to mention it briefly, but in the near term, we can sell into existing markets. So the, you know, existing uses for HCl, where what we are providing is much lower cost than current HCl and 0 carbon footprint. So that would be the advantage, like why you would purchase what we're selling. Medium term, then because it's low cost, we can look for certain areas where maybe other acids are used, but hydrochloric acid could be used. One of those is production of phosphate fertilizer. So sulfuric acid is used, you can use hydrochloric. People probably wouldn't switch if the price were the same, but if the carbon footprint is lower and it's much, much cheaper, they probably will. And then longer term, there's a lot of overlap with Ben's talk and Greg's. So we're working with Pete's group at Penn, looking at using that acid to enhance the kinetics of some of the mineral carbonation into mine tailings. And then also in some of the mineralization approaches, kind of like Ben described, where you're putting CO2 into basalt, there's some concern that potentially the kinetics in large scale injection could slow down. And so you could release cations with acid to help with that. So we're kind of actively looking longer term for new markets. So for sure, like to get to gigaton scale, we need new uses of it. And then the question of making sure that the hydrogen ions don't make it back to the ocean to mitigate, which would just negate what we're trying to do. In all of the cases where we're looking at the use, it's either if it's it's something that's going on now, then it's baseline. And if it's a new process, yeah, making sure that at the very least, it's 1,000 years before it migrates back.
Okay. And a final quick question from Don Lawton, and he's the Scientific Director of Carbon Management Canada. Are there good ocean mixing models that show the rates of dispersion of the alkaline solutions prevent local pH dramatic increases that would be a problem for biota and other stuff? So are there any limits on point source discharge of your alkaline solutions? Yeah, so on the modeling aspect, I'm not sure, but I do think, you know, in working with our modeling partners, I know getting to that smaller spatial scale is something that's on the roadmap, but we're directly measuring as well. So that's why at the very local point of where we disperse the alkalinity, we'll be monitoring the chemistry and using that as a feedback system. Also, that's why I was trying to be clear. It's not like we're putting half molar NaOH into the ocean. We're diluting it first to be essentially a relatively high pH seawater that we're then putting in. Yeah, great answer. Okay, so that was tremendous. Thank you. So we're going to move straight to the panel discussion, please. And the panel are appearing. There they all are.
Matt, maybe you stop sharing your screen.
Okay, there we all are. So limited time, but lots of potential questions. So I think we'll kick off on this. I think all of you are involved in startups in one way or the other. So yeah, the question might be something like, the techniques you've been describing all offer great potential for tackling the climate problem, but they all seem at relatively early stages. So in the culture of innovation and startups, one of the most important steps is to keep pushing forward good ideas and letting old ones go, you know, the fail fast kind of startup culture. And this is something that's particularly difficult for academics to do in some settings. And we tend to end up with our pet projects and so on. How do you balance now, especially in a situation where you've got lots of climate tech capital potentially available? How do you balance the quest for the technology with the potential distractions of commercial outcomes in the short term? How do you deal with those challenges? Maybe start with Greg and then go to Matt.
I'm not sure I understand the question. How is getting commercial funding a distraction to do what we need?
Maybe the question is it? Or, well, so maybe that is the question. Do you think the fairly ready availability of commercial or investment capital, is that a distraction to your sort of, let's say, medium to longer term research goals? And how do you balance those interplays?
Yeah, well, clearly we have R&D needs that need to be funded, and that's how we use our money. Clearly, we don't, you know, you could probably envision over investing in this and investing in a lot of stuff that maybe shouldn't be invested in. Maybe that's what you're asking. But you know, in our case, we try to, you know, very carefully outline what it is we need to do, where we are today and where we need to get to, and what it takes to get to where we want to be. That requires funding and capital, and that sort of dictates the size of requests that we would make to investors. We don't want to go over, we don't want to overpromise, and we don't want to get more than our technology justifies, and we don't want to get you know, low TRL technology and fund that at say TRL 9 levels, or very, you know, assume that we're going to make a huge jump. So it does need to be measured, and yeah, that's something that I think each company has to judge, and each investor has to judge how much to put in. And you obviously want to do that strategically and in a way that maximizes your return on development of technology and ultimately return on investment.
Thanks. Matt.
Yeah, it's a good question. I mean, we feel, after analyzing it from all angles, that we have an approach that has a real chance of making a difference, right? So, and then we sort of objectively say, what are the things we need to de-risk? And like Greg said, we actually want to take as little money as we need to do that. And if in that process we find out it's not a good idea for this reason, or it just can't scale for some reason, then we'll stop and do something else. And I think actually your question, you mentioned also the research commercialization, you know, kind of university or scientific research and startup interaction. I think it can be really beneficial, right? Because they definitely feed off each other. You learn things in one that feed on the other, but then also when you have sort of a longer term research program, you're more willing, if the startup approach, if you decide that it's time to not pursue that course, I think you're more likely to do that because you'll go back to your longer term research plan. And you know, to your fail fast question, I have plenty of examples of that, but like the predecessor of this for me was, we worked on something called Project Foghorn at Google X, and there it was similar. I can't remember who showed some slides of similar processes today, but there we were doing the similar electrochemistry, but to do pH swing to strip CO2 gas out of the ocean and make a liquid fuel out of it. And when we did the economics on that, it was just way too expensive. But as part of and so we stopped doing it, we killed it. But as part of that, we realized if all you cared about was the CO2 removal, that part of it, which is basically the electrochemical part of it, is actually pretty cheap. And then it's only the development of this voluntary carbon market where people are willing to pay for exactly that, then it was the time to pursue doing that piece of it, basically where we store it as bicarbonate.
Yeah, no, it's great. Yeah, I mean, I think you know, the research, discovery, and innovation solutions, they're synergistic, right? If done well, and you know, a lot of positive feedbacks. So yeah, Dave, any thoughts?
Oh, sure. On the point of academics, you know, getting stuck on our pet projects, I think it's a big challenge, and I think we should be asked, Steve, every year, you know, what did you change this year in your research directions as a result of new realities or your own progress? You know, how are you moving? Because I think we need that. I think also on the other point on industry, I think industry helps us do that a lot. It's, you know, a good industry, deep industry collaboration. I think really is a secret weapon in academic research, not just because of money, but because good industry collaborators will help you find the right problems because they have a view to that that you'll never get at an academic conference.
So let's change topics a little bit. And we've talked about social license, social desirability. Anna Maria talked about getting I'll call it society in a broad sense involved up front, right? Rather than technology developers going to society and asking for license. What are the advantages, disadvantages, and processes that we might involve to better engage society up front? So maybe Anna Maria, if you could kick off quickly on that, and then we'll again go around the houses.
Yeah, sure. I'm still stuck a bit on the last question, which is, I mean, the big question here is who decides what the requirements should be or how we move ahead and pursue innovation. And so, I mean, the current model is taking research to startups, and it sort of comes down to an issue of corporate responsibility, which is a big piece of governance here. And so we see different kinds of requirements being imposed either from within a team, which is something that we have been thinking about within the context of Peach, but also, you know, for example, Stripe Climate, they have a process for vetting projects that they'll fund. But again, the sort of question here, and that's sort of how the model has always worked, there is a conflict of interest between, you know, that I think researchers have when they're commercializing things. There are a lot of like terrible ideas that are economically viable in the world. And so, yeah, I am a little, I think, again, it comes down to the question of who decides, and it's kind of the Wild West, I think, when we think about governance. But I do think it's important to ask the question, you know, and this is, I think, a research question for social scientists. You know, what do people foresee as the issues with these technologies? What sort of are the values in which we use to how they should be implemented? For example, you know, we have net zero commitments from a lot of oil companies in the oil sands. How are they going to meet them? Well, CDR will probably be part of that, but you know, how will they feel about it? You know, off the coast of BC, sort of supporting the infrastructure and all the potential risks that go with implementing it. These aren't sort of straightforward questions, and they involve different spatial and scales and different actors. But I think we do need to make best efforts in sort of doing that research, and it's still at a very nascent stage in terms of what are the societal dimensions of the development and implementation of CDR. And we have to sort of make best efforts to incorporate what we've learned, including from other analogs, blue carbon, deep sea mining, and so forth, to integrate that information as part of sort of the broader governance question.
So Ben, in solid carbon, I mean, this is, I know, part of your sort of discourse in the project. How are you approaching these issues?
Yeah, I think it's a really great question. I think there's a lot of these things that I would say that scientists aren't really even wired for, you know, to begin with, to think about. And what has, from like conversations with Terry Satterfield, who's a really smart scientist at the University of British Columbia, that has basically convinced me that like you as a scientist think in a certain way, and you cannot assume that the public thinks anything like that, right? So we, for example, know that there's very little risk in solid carbon of having hydraulic fracturing or something like that to occur, or stimulated earthquakes or something like that. But that seems to be the first thing that people think about whenever we're talking about injecting CO2 into rocks, right? And it's right away, you know, and so like this thing that we think is a total non-issue is an enormous issue to the public. And those types of things are things that we all, again, need to think about right up front, right? What is the problem? Don't get off on the wrong foot and then never be able to recover from that as your technology develops.
Yeah, good points. So, you know, both Matt and Greg, you've both had substantial external investments. How have you tackled this kind of social engagement, social license slant? And we'll go first, Matt, and then we'll finish with Greg.
Yeah, so I mentioned some of the mesocosm experiments that we're starting. So we're working with academic partners to really just study the effect of this, even though it should be, you know, we're returning relatively benign, high pH seawater, nevertheless, to study the effect on, for example, phytoplankton communities or marine organisms, and really just get data that we're convinced that it's safe and it's actually probably beneficial. But that's really our approach. And I think there will be when we'll have the field test unit out for CMATE soon, and I think that's an educational opportunity, right? So I think bringing people to see it and explain what's going on is probably a big part of it.
So we'll leave the last word to Greg.
Yes, well, obviously society should have the last word as to whether or if we employ any of these technologies. So, I think the technologist's role here is to make sure that we supply society with effective CDR that's worth arguing about whether it's socially acceptable or not. There's no point in wasting time on approaches that aren't going to help solve the problem just from a amount of CO2 or capacity standpoint or economics or whatever. So it's important to, first of all, find out what the viable technologies are. And we're still, in my view, in early stages there. There's a lot more to do. And our job is to provide information about our respective technologies so that society can make intelligent decisions as to whether this is worth doing or not. And certainly early on, we need to engage social entities in this, inform them what we're doing, why we're doing it, how we're doing it, trying to do it as safely as we can, ask for input on how we could do it better, et cetera. So I think it does require outreach and interaction, but I think society needs to be reassured that they're going to have the last word here. It's not us. It has to be acceptable to all of us to move forward, and there has to be decisions made by a group way outside, the group that we have here today. And so I think what's needed is assurance that that's going to happen, and also inclusion in these other entities to make sure they understand what we're doing, why we're doing it, and why we need to do further research to provide them for information to make intelligent decisions.
Yeah, and of course we're part of society. We're voters and citizens as well. So we all have a vested interest in positive outcome. So we didn't manage to get everybody involved in the discussion, and that's just tempus fugiting. But I'd like to thank all of you for your contributions, and I'd just like to just share a thank you slide for the people who put the webinar together, which is kind of the Peach team, and then Melody Harris, who pulled the webinar technology together. So I thoroughly enjoyed it. I thought there was a tremendous set of presentations and some good discussions, and thank you very much. That was an excellent morning. So thank you, and here's a hand clap to you all.
Yes. Thank you.
Bye-bye.
Thanks.
Thank you.
Thanks, everyone.